So thank you, for introducing me to the audience. Okay. So first of all, I would like to thank Dr. Kalyan, for inviting me to this workshop. And I think, this workshop is on earthquake engineering and seismology. And I have seen, I think there are sessions on earthquakes, ground motion prediction equations, ground response analysis, and so many other things itself. And of course, Kalyan has, asked me to speak on machine learning applications in earthquake engineering. Okay. So unfortunately, what happened was last 5 years back, we have also started working in this area, like some PhD students, they worked, and then, we have developed some, these machine learning models. Okay. So for predicting earthquake strong motion data, and then of course, nowadays we are making it advanced, like to model, the time histories, as well as earthquake source models and other things, etc. Okay. So today I will be showing you some of our results and some brief, these things also. Now, so you are able to see the slide, right? So slides are visible?
Yes, sir.
No. Okay. So anyway, so now, so this is what the title is for the today's talk. So that is artificial intelligence and machine learning techniques in earthquake engineering. Okay. Now, before I go into these details, okay. So now today, I think full day we have a session. I think 9:30 to 11:30. Then I think 12 to 1 some, and after afternoon session also we have. So what I will be doing is, I will have whatever I'm my talking say. Okay. So whatever my talk, I have divided it into two pieces actually. The first one is a shallow neural network, which I will be covering in the morning session. So shallow means, it's a very simple neural network and very classical, things, okay, which, people have used in the past. Now also, these are very simple networks. Okay. So where one does regression analysis, supervised learning, nonlinear regression, so all these things can be done with this shallow neural networks. Now in the second lecture, say that is maybe in the afternoon or maybe sometime, so I will be covering this deep neural networks, which are, the emerging kind of thing, and which have a lot of applications in earthquake engineering to reduce the dimensional reduction, non-linear principal components in auto encoders. And of course, I also will start with some basics of earthquakes, and then I will show why, these things are also required in earthquake engineering also. So now, of course, in one day, you people will not be able to understand, what is happening or what is this one. So I would suggest, if some of you are interested really in this subject, say, so you can, there are of course a lot of textbooks. Then I think in YouTube also, if you type, so many videos and so many things are there, and so many books also are there. So I suggest all of you to read this, this book actually written by William C. I think he's a professor. He's retired in, some British Columbia, I think Canadian professor. So he's written a book on machine learning methods in environmental sciences. Okay. Which you have all the fundamental basics he has covered nicely in this textbook. Okay. So it is Cambridge University Press. You can buy online or soft copy or hard copy. So I suggest all of you to go through this textbook itself. Now, of course, there are other textbooks also are there. This will be easy to follow, because we are civil engineering, and it's easy to follow this textbook itself. And there are a lot of videos are also there, in YouTube, which you can see. Then now, so generally for neural networks, no need to write any code itself, okay? Because MATLAB, they have already a inbuilt toolbox is there. Just if I will show you also 2-3 lines, you can write your own network, you can solve the problem itself. Then now Python is emerging, I think there we have this TensorFlow and other codes are there. Then I think Jupyter notebooks or something. So many toolboxes have been, already available. And nowadays, what is happening, in many of the international journals, say, whenever you publish a paper on neural network, so it is mandatory that, you have to share the code also, and then the data also, because the reviewer, can verify whether you are done correctly or not, So what happens is many of the recent journals, they are giving the code also, and they're sharing it in a GitHub platform or some website. So you can directly get those codes itself, and even the data also, because for transparency, it is becoming mandatory nowadays. Okay. So all these details are also available online. Okay. And today, in the afternoon, say, that 2 to 5 session. In the last 1 hour or half an hour, my one PhD student is there, so Mr. Srinath, so he will show you a live demonstration also, like, how do we run a neural network in MATLAB, how to write the codes. He will show all the procedures also. Okay. So that will be in the afternoon, in the end, we have planned such a way this entire, session on machine learning. Okay. So fine. So now I think this is what the tentative I have introduced to what I'm going to talk today. So shallow, then deep, and then some demo session will be there in the afternoon actually. Okay. So now let us go to the basics or some of the introduction. So like for example, and why artificial intelligence and machine learning, why we have to study this subject and in how it is connected to our earthquake engineering also. So this is a fundamental question which everybody, comes into our mind itself. Now, if you see this artificial intelligence and machine learning, see nowadays it is a most the popular subject actually. Okay, so of course neural network, these things was there long back in 1980, 1990. Also, we had a lot of papers got published, on a neural network in civil engineering. So many papers was there. But after that, that subject became dead. Nobody was interested, and that subject, it was not active during those time. But recently, in the last 4 to 5 years, once again it has picked up this machine learning, artificial intelligence, and all other research also has increased in this area. And nowadays, if you see many IITs or NITs or even engineering colleges also, they have started, BTech programs, you see, on data sciences, machine learning, and even I think there are a lot of diploma, so many courses and so many things are there, where the subject has been offered as MTech elective or BTech or something like that also. Okay. And even if you want to offer a course, say, in machine learning, the classes will be full nowadays, so all BTech students, everybody, irrespective of their branch, they may be chemical, they may be civil, they may be mechanical or anybody. So all of them wants to learn this subject itself. Okay. And even the employees, say, so like many software companies who are working employees, or even, nowadays slowly civil engineering also has started. They also want to do this type of course. So they are enrolling for a diploma, other courses also. Then of course, researchers also, like PhD students, MS students, say, the new students also, there has been an interest actually, okay, in working in this area itself. So it is a very popular subject, nowadays. And of course, job opportunities also, if you see, so now outside, many companies, they are recruiting what they call as a data scientist actually. Okay. So you may be civil or mechanical or whatever. So if you are very good in machine learning and artificial intelligence, many companies, any company, they are doing this data scientist jobs. Yeah. So now this, and of course, they are also paid very highly also. So that is why this subject has become very popular, nowadays. Okay. So now if we see these applications of artificial intelligence and machine learning, okay. So now, a lot of applications are there already nowadays. Okay. So you would have also experienced in your, life itself, like when you're doing web search, automatically this algorithm is already embedded. So if you have clicked some software, say, automatically Google shows similarities and other, things also. Then in e-commerce, say, like Amazon, whatever, so if you're interested in a product, it automatically pops up those similar things to you also. Then we have in space exploration, say. So in space exploration, there is no way, you have to use artificial intelligence only, because if you have sent a rover, sending a communication itself will say hours. So, you have to embed these in the chips itself, so that, they can take their own decisions actually. Okay. Then in computational biology also, say, a lot of applications are there, and many companies, people are using it in their things also. Then social networks actually, Facebook or many, this also a lot of applications are there. Then of course robotics actually, okay, which anybody, everybody, like you would have seen that which cleans the floor, many, mopping things, so many, they have incorporated this artificial intelligence and machine learning algorithms also. Then even in image and signal processing, say, okay, so like, by looking at image, it can detect, the what is written on that, whether the image is a fake or not. So many applications are there, nowadays. But when it comes to civil engineering, say, so this most important thing is, in civil engineering, there are a lot of papers have been published, research papers, okay, on handling, predicting compressive strength of concrete or handling earthquake data. Lot of things have been published. but there has been no applications in the practice actually. Okay, so when you do any practical application, neural networks, people have not used in the past. But in earthquake engineering, say now slowly, because the data is more, now in our hazard analysis, say slowly, people have started using this, the GMPs or whatever, which has been developed from artificial intelligence. Okay, in the last 2 years, a lot of papers have come and people are really using actually, okay, in hazard analysis, and then to find out, say, site specific ground motion. Okay, so site specific, UHRS response spectra, polar amplitude spectra, to derive these things, people are using these machine learning algorithms actually. In the past, there was no confidence on these numbers, but now confidence level has increased and people are really using it in the practice actually. Okay, so I will show you some of those things itself. So now generally, you have to understand what is the difference between machine learning and the conventional techniques actually. So generally in our civil engineering, say, whenever you want to solve any problem, it is a beam or a column or even earthquake engineering also, if you want to solve any problem, say, the conventional way first is, the equations of motion actually. Okay, so these are mandatory. So generally, whenever you see a beam, say, immediately, all of you will recollect this simple building formula, M by I, E by Y, sigma by R, or some F by R or whatever. So the simple bending formula you realize. Suppose if it is a plate or any complex, say, we write, these stress equations of equilibrium actually. Okay, so this is our starting point. So generally in civil engineering, so in your undergraduate or whatever you have studied, say, structure analysis or whatever, the starting point is equations of motion only. Then you will have some boundary conditions you have to put, like simply supported, say, deflection 0, bending moment 0, something like that. And finally, you get the solution actually. Okay, so and you will get the displacement or whatever quantities are there. So you try to solve it. Now, simple problems, you will get analytical solution, but if they are complicated, say, you may have to do some finite element model, all other things are there, and then we get our solution. So this is a conventional approach actually in our civil engineering. If you want to model even earthquake also, we follow the same procedure itself. Now the limitations of conventional approach is, the assumptions basically. Okay, so the lot of assumptions have been done to get these equations, and we assume this homogeneous linearity and all those things in our calculations. So what happens in reality is, when you do conventional approaches, say, the solutions are easy, it is very easy to understand all those physics, everything can be this one. But when you try to compare this with the real data, say, and of course when the loads are very small, maybe they may be giving a good comparison, but when during failure or when the loads are increased, say, then we have problems actually. The conventional methods, there will be a huge difference in our solutions itself. So what we do in our engineering, civil engineering, because many times the your conventional things, they doesn't agree with the experiments also. Okay, so what one does in civil engineering is, like whenever you see the building codes, say IS 456 or IS 800 or all the design codes, what happens is you will see a lot of formulas actually. So most of the formulas, they have come from experiments, not from the conventional studies itself. So what one do in our civil engineering is we do a lot of experiments. Like for example, we test beams, then columns, then we have you followed it lateral torsional buckling, or I am just showing you some images. Lot of experiments we do in civil engineering, and we generate data actually. Okay, lot of data from the experiments itself. Suppose if the nowadays finite elements have advanced like that. So if you are unable to do experiments, say, you can do numerical experiments. Like in finite element, you can incorporate nonlinearity. You can generate data from finite elements also. So you will do a lot of data here. And from this data, say, you use statistics actually. Okay, some type of formulas you can derive. And of course, the functional forms, what type of, whether you have to put y is equal to mx plus c, or quadratic or cubic or 3 by 2 or whatever is that one. So we take from little bit from mechanics also. Like we know, if it is a simply supported beam, if the load is concentrated load, say, so then bending moment diagram is linear. Suppose if it is this one, so bending moment diagram will be parabolic. So already you know the functional form, x square or x cube or x to the power of 4 or whatever. So you take some functional form, the polynomials or whatever, a little bit based on mechanics, and then you fit it to the data, and then you derive a equation, and this equation goes into the code books actually. Okay, that is how we try to do it in our civil engineering. So in our civil engineering, say, so the most important approach is whatever you have studied, what we follow right now is a conventional approach, writing equations of motion to understand the physics of the problem. Then because this doesn't match very well with the experiments, you do a lot of experiments, you generate data, you fit both of them or whatever, and then you derive something and then use it in the design or use it in the practice actually. Okay, that is what right now the procedure is in our civil engineering. Now, when it comes to loads, say, like, how to calculate the design load. Like, for example, I'm showing you the wind zone map here. Okay, the zone map which has come up from the winds actually, right? Some, I think, 6 zones or something, the whole India is divided into zones. And if you see the IS 875, I think part 3, a lot of formulas are there for wind actually. Okay, so many these zone maps, if you see for wind or zone map, these all have been derived from, the data. They have not done from mechanics actually. Okay, so people have instrumented the wind, say that instrument is that they calculate wind speeds, and then they do from the data, so some statistical analysis, and then they draw this zone maps actually. They classify zone 1, zone 2, and then these are the design the wind speeds actually. So everything has come from the data only, data and little bit of some probability statistics and other things. Okay, so this is how this load calculation happens, and lot of formulas in our wind codes, they have come from the experiments like wind tunnel tests they do. So you would have seen all these type of numbers and formulas will be there. So so in the wind load calculation, say, it is a very less mechanics actual, and mostly everything is governed by data itself. Okay, so this is the most the important thing for wind code. Now, similarly, earthquakes, which anyway this symposium is about and which we are all interested here. So if you see how the zone factors, so that Z value you would have already seen in the code actual, how this has been arrived or how the zones have been derived, say, everything has been derived from data only. Okay, so there is no mechanics, everything comes from the data. So like epicenter data, or it may be damage data, or it may be whatever it is. And of course, the old map is based on damage data. So based on the MMIs and other ones, say. So these boundaries have been drawn actual. Okay, so there has been no mechanics, nothing here. And even the formulas, like for example, how to calculate time period for RC frame building, steel frame building, all these formulas also have been got from the experiments and all other things itself. Even the response spectrum shapes, which you have seen in the IS code, okay, you would have seen here also. So this also has come from data only. So we collect data of all past earthquakes. You normalize them to 1G, you just average them, and then you smoothen them, and finally you will get a beautiful spectral shape like this. So mechanics, very little. So everything is based on data itself. And even in our code, you may be seeing, suppose if you have any important structures, tall buildings, dams, or power plants, or even the temples are very important structures, they say that you have to do site specific response spectra actually. Okay, so this itself, hazard analysis, everything is based on data only. So based on that, you have to get the spectrum, and you have to compare with IS code, whichever is higher, you have to do it, you use it in our design. Okay, so this is a practice actual. So right now, so now, so what we are trying to, what I am trying to conclude is, so traditionally in our civil engineering, say, the methods which you are following is, one is a conventional approach, then the data actual, and then you have data, you do some little bit of statistics and something, and then do our calculation. So these existing procedure are the existing approaches which we have adopted in our civil as well as in our earthquake engineering. Now, why artificial intelligence you followed, right? Why recently only AI or this machine learning came into picture? So that has become popular in our, our civil engineering. The reason is like this. Nowadays, what's happening is now, that's what I told. So full experiments, this is important for IS codes. So now this has suddenly, peaked up actually in civil engineering. The reason why this subject has picked up is in our civil also, the sensors have become very, very cheap nowadays, So like if you have a strain gauge, say, so I think a good quality strain gauge you will get for 500 rupees or 100 to 200 rupees itself, you can get strain gauges in the market actually. And nowadays accelerometers, which was once upon a time very expensive, and availability was not there. Gyroscope, GPS, all those things are available at a very, very cheaper price. And all of you are having mobiles, your mobile itself contains all these terms itself. So if you spend 200 rupees or 300, so you can buy an accelerometer, which is, of course, sensitivity maybe plus or minus this one, but you can get a very accelerometer even for 100 rupees, 200 rupees also, gyroscope, GPS, they have become dead cheap actually. So now once the things have become very cheap, say, now people have started buying and doing lot of experiments in, their institute itself. See, when I was doing in my bachelor's program, to test a concrete beam or a column, it was very difficult, and we were unable to, we were unable to do it actually. Okay, maybe in the whole batch once or something like that. Okay, the equipment itself was not there. But now, if you go to any private college, you go to any small institute also, they have a huge experimental facility and a lot of PhD thesis. If you see, they do compressive strength, they test a beam, they test a column, lot of data is getting generated nowadays in our civil engineering also, because this is the reason. That's due to the sensors became very cheap actually. And so large amounts of data has been generated. So if I collect compressive strength cubes or whatever, or other beams or columns, huge data, IITs, NITs, local colleges, everywhere they have a good experimental facility, and they have started generating lots and lots of data itself. Now, apart from that, say, nowadays, what the another advantage is high performance computing actual. Okay, so this also has become very, very cheap. See, right now the mobiles, say, the what you are carrying in your pocket itself has 8 GB RAM or 6 GB RAM, So 1980s, the supercomputer had a 6 GB RAM actual. Okay, so the 1980 supercomputer now we are all putting in our pocket, and the price is also 10,000 rupees or 15,000 rupees. The high performance computing has become dead cheap actual. Okay, so everything has become at a cheaper thing, and then experiments are also becoming very cheap. So now people have started generating lots of data, and computers are there, say. So now so this has made this subject to look at this data from a different perspective. So whenever we have data, say, we look from conventional perspective or we look from statistics perspective. So now the question is, since large data is there, say, can you look at the data from artificial intelligence or machine learning perspective is the question actual, which was asked by many researchers, some 4 or 5 years back, and that is how this subject has progressed, very nicely in the recent years. And this is just, one small, this equipment instrument I'm showing you. It's developed by one small, a startup company recently. So this is just a small instrument actual. Okay. So you can monitor you can put it in just in your pocket, or you can even stick it to some place. It measures, the motion sensor, the noise sensor, the temperature, the ultraviolet, everything. It's just like a small instrument itself. And this is the of the pocket. If you buy some part of it, so if you have, or you can carry it in your pocket, it gives you lots of data itself. And then recently new instruments have come, rotational sensors actually. In our civil engineering, generally we have strains we measure or deflection we measure. Now instruments have come which can measure the rotation also. Okay, so like for example, if I have a beam and column, say, okay, so if you put that instrument, this rotation also you can measure from these instruments. And the sensors price is also something like 500 rupees. You can buy these sensors itself. And then soil profiles, because I think somebody in this symposium, somebody is talking also on ground response, like the shear wave velocity profiles, MESW equipment. All those equipment was very, very expensive previously. But now, you can get it for, I think, 10 lakh. Once upon a time, 30 lakhs, 40 lakhs, you have to shell it out. Now you can do for 10 lakhs this one. And if you can develop your own sensors, say, just from your mobile also, you have an accelerometer. So using those equipments, even in 1 lakh or maybe 50,000 also, you can develop these type of equipment, and you can characterize the soil profiles also. So that much, cheap, you see, the sensors have become. And if you develop on your own, it becomes much, much cheaper compared to the market. See, the market price MESW, say. So this equipment, some 10 lakhs or whatever you may have to spend right now. But if you can devise your own devices, if you buy from Chinese or whatever this one, so and if you can develop, say, you can get it less than 1 lakh or even 50,000 also. You followed. So because all the instruments are there, the chips and other things also. So this is the reason why the subject has become very, very cheap. Now, since the equipment is very, very cheap, so people have instrumented left and right actually. So this is one tower, the Canton Tower say, okay. So in, this somewhere in China, Guangzhou or whatever. So this is a tower actually. So now what people are doing is tall buildings and others, you have to monitor them also. So what they have done is here they have put up in this entire tower, so they have put up lot of sensors like weather station, which can measure temperature, humidity, rain, air pressure. Then they have anemometer actually, which measures the wind speed, direction, and others also. Wind pressure, accelerometer, 22 accelerometers they have put up on the all the floors and even the ground floor. Then seismograph is there, wire gauge, thermometer. You can see fiber strain, optical fiber, GPS, digital camera, laser, tilt meter, corrosion sensor, which is very important for the steel. Then total station, theodolite, all these instruments, this full building has been, instrumented completely. And these instruments also, they record every, like you see, 10 samples or maybe 100 samples per second. Huge amount of data has been generated actually. So now this is this one. And then you also know this is famous, right? So this tower is Burj Dubai Tower. I think many of you would have gone, and this is an iconic building, right, in Dubai, the tallest building or whatever. Now this building, the whole building has been instrumented actually. So they have put up instruments like meteorological data, displacement data, tilt meters, so everywhere, seismographs, all it has completely instrumented. I think they have put up these instruments in all the floors also. So now once, and these instruments have also started recording like say every 100 samples per second or something like that. And finally, if you see the last 5 years, you have data something 100 terabytes, 200 terabytes, 500 terabytes of data is available nowadays. Okay. Now the problem is, how do we analyze this data itself? So now that this data may also, you have to analyze this data properly, because if there is any damage in the structure, say, so automatically, this day you should be able to identify those damages from the data itself. Because if you identify the initial stage, then repair of the building may be very cheap actually. But later, if you delay, the damage will progress and it may lead to other, issues itself. But the problem is, the 100 terabytes or 500 terabytes, and you are getting data from variety of instruments, like you are getting from accelerometer in all the floors, you are getting this information from wind pressure, all meteorological data, a whole bunch itself is there. And using this data set, now you have to take a decision actual, or you have to identify, what is happening, whether anything repair rehab required or not. So that is what we call as a health monitoring of the structure itself. So that is where the problem comes. So huge amounts of database, say. And of course, I just showed earthquake also. Even if you see the rainfall, say, nowadays a lot of instruments have come up which measure rainfall. You would have seen also, even in Facebook, many weathermans, many people claim that they're weathermans by looking at the images. They give a lot of forecasting, so much of information. Even I think in Hyderabad, huge rainfall is there, in Chennai also. So the forecasting say, so this also a lot of amount of data is there. So now you should be able to take this data, the cloud movement, this data, that data, and finally you have to come up with some type of a decisions actually, So this is why the things are becoming very, crucial, in the decision making itself. Now coming to our earthquake engineering side, which is of interest to all of you. Now recently, what has happened was ground motion data, like the acceleration time histories are the starting point here itself. So now a lot of instruments have been put up on in the world itself. So these red dots which you are seeing here, say, okay, so they are all the seismographs actually, which are right now working in the entire world itself. Almost, I think in India itself, you can see huge dense networks are there. And if you see US, it is extremely populated. I think every half kilometer or every meter level itself, you will have a seismic instrument. And if you see Japan, say, Japan, Taiwan, Japan, I think they have put instruments on the surface. They have put instrument below also. I think every 50 meter or 100 meter itself, you have a seismic instrument. Now you can see this is South America, say, the full, it is a highly instrumented places. So more than 1 lakh or 2 lakh or more than maybe 10 lakhs itself, we have a lot of instruments are, are working all around the world itself. And generally in earthquakes, say, so this data only is the starting point, because we know earthquakes only from their ground motions only, because nobody has gone inside and seen, how the fault looks like or whatever. So we know earthquakes only from the data. So since this data is very important, say, So people have instrumented and started recording this data. Of course, the sources are buried deep or whatever here. So now in our earthquake engineering say, so generally in civil engineering, I showed you conventional means equation of motion, you write and you do all those things. In earthquake engineering say, we have conventional method also, but that is not widely used. We use this, the database and data analysis itself, that is a ground motion and other things only we handle, in earthquake engineering itself. So the empirical models, say, which are based on, the data and widely used, we use this in analysis and design itself. And of course, mechanics, is little bit used, but entire thing is based on data itself. And now if you see all the instruments, say almost, if you count 10 lakhs or more than, 20 lakhs or 30 lakh time histories are available right now, in our, in the global database itself. And these are some of the instruments actual. Some of you can see here. So this is a broadband seismograph actual. Okay. So variety of instruments also have, been evolved recently. So this records, the velocity ground motions actual, and it can record, the low velocity, low this itself. And this is a strong motion accelegraph, the Titan instrument. So this also, it records strong motion. This is a new instrument actual. It can record both broadband as well as a combination of these two, and it can record very low frequency to high frequencies. That's a recent instrument manufactured by Japanese actual. And this is also one more accelegraph I'm showing here. Say 10-15 years back, say the cost of these instruments was extremely high, 50 lakhs or 60 lakhs or something like that. But now, with 1 lakh or 2 lakh itself, you can buy this instrument itself. And now, as already I told you, if you can, these are made by the companies. So if you can, develop your own equipment, say, with buying some equipment from other countries or whatever, so you can manufacture your own seismographs for less than 50,000 or maybe 10,000 itself. You can manufacture your own seismograph and other things also. So a lot of instruments have been done, and so much of data is available right now. So this is what I'm showing you for the Japan. You can see all these dots show the instruments. They have a broadband, they have accelegraph, they have all kinds of instruments have been put up. So like if I take a particular station, say, I have data from broadband instrument also. I have data from acceleration also. So I have velocity also, instrument which has recorded velocity, and I have instrument which has recorded acceleration also. And acceleration, velocity, right, the relation. If you differentiate velocity, you will get acceleration. So now you are getting like a duplicate kind of thing, you are getting this also, you are getting that also, you followed. So like that, so much of information is available nowadays. And he's in India, you can see. So this is one of the, the network. I think 5 or 6 or 7 years back, IIT Roorkee, they have installed all the instruments in the Ganga Basin and in the Himalaya and Northeast India. But right now this is being monitored by Ministry of Earth Sciences actually, or NCS, they say, National Center for Seismology. They are monitoring instruments. Apart from that, they have instruments all over Gujarat and other places also. So dense networks and data has started pouring from all these networks itself. So now this is a very important figure to show why artificial intelligence is required. You can see this is a typical recording from broadband instrument actual. Okay, so this is a broadband instrument. So these instruments, it records continuously actual. You can see starting from 0, it is 1 day data, that is a 24 hours data set. It keeps on recording itself actually. Now what happens is, when you look at this data will be like this. Okay, so now when you look at this one, say, so what happens is these large things actual. So these big things, whatever you can see here, our human eyes, say, you can easily recognize it, and if you zoom it, you can get this type of data. So human eyes actual. Okay, so what happens is our human eyes can detect large events basically. Now this small, you can see here, this small thing, or this small, whatever you can see here. So this what generally do is, as our humans, we can't differentiate basically. Okay, so what we generally do in our instruments is, whenever the small oscillations are there, say, we say that it is a noise or something, we ignore them basically. Okay, so our humans, we cannot detect. So large things we can detect very easily, but small things, it's very difficult for us to understand them actually. And if you are working in earthquake engineering, say, so most of you know, right, like these small things, say, so they may be a foreshock, they may be aftershock, before a large magnitude earthquake. Small earthquakes will occur actually. Okay, so their amplitudes will be very small itself, and once a large magnitude has occurred, say, then also small adjustments will take place, and small things will come, which we call them as the aftershocks. Okay, so they automatically this comes. Suppose if we understand, say, from the data, like four shocks, if we understand that they are the four shocks, then you can easily forecast actually. Okay, these are all four shocks, say. So definitely after some point of a time, so there will be a main shock. The magnitude will be very high, so we can give even a forecast, or you can give an alarm actually. Okay, so such and such huge earthquake is going to happen or something like that. But generally in our humans, what happens is the large things we can detect, but our human eyes, the small things, we cannot understand. And the data is, now he's at one station. Suppose if we are having at several stations, say, then it is very difficult for us to understand and then process this type of data itself. So that's what. So this is where the humans fail and the computer gains advantage actually. Okay, so humans, whenever you look at the data, large things, easily we can identify, but small things, we cannot identify, and we call them as noise, and we ignore them in our the calculations or whatever. Okay, and these are very important for forecasting or predicting these earthquakes itself. So this is where the neural networks comes into picture actually, in handling these type of data, in understanding this small things also. And if the data volume is also very high, say, so this becomes a lot of artificial intelligence has advantages over our the conventional or this approaches itself. Okay, and of course our seismic zone maps, a huge data set is there. Okay, now using that huge data set, now you have to identify the zones, the clusters, and other things also, and then you have to get this response spectra itself. So this is the most important challenge actually. Now, 1 second. So you can see, so this is our the global seismograph networks actually. Okay, so which are monitoring continuously 24 by 7. So they will be recording the data, and then they will be processing, and they will be doing all the calculations also. Okay, so now what has happened, because lot of instruments are there, lot of earthquakes have been recorded. See, like for example, in America, say, so many, we have data from all these earthquakes. Actually, in Japan is one of the best network in the world. Of course, I have not. I will show India separately. So New Zealand, so lots of data sets have been recorded with this one. Okay, and if you plot them as a function of magnitude and distance, you can see huge data set is available. So this is our famous, the NGA West 2. Okay, and this data set is available online. Okay, so you can download this data set. It's a flat file, they say. So where the response spectra and others has been given already as Excel sheet. You can download and you can process this data itself. So now if you see, you can see from 3 magnitudes, say, up to 8 magnitude, all the data is available at all the distances, and for variety of faults also, like strike slip, normal, reverse oblique, normal oblique, and we have data coming from variety of site classes also. So total something like 13,500 data sets are available from NGA West database, and this has only shallow crustal events. Okay, so the shallow crustal events are also available. So now apart from that, say, so we have what we call these are something like NGA East, they say. Okay, so this comes from stable continental regions. Okay, so like for example, peninsular India or the Central Eastern North America, say, so you have data. So here we don't get large magnitudes, we get only 6 or 7 these type of magnitudes. So you can see huge databases, the available something like 10,000 data points or whatever we have. Like, and if we include some other data sets also, huge databases are available in our NGA East also. Now this is our Indian things, as already I showed you. So in India, say, you can see these these rectangle triangles which you are seeing, they are the data instruments actually, where the instruments are located, and these are the earthquakes actually, for which we have recorded the database also. Now this is in Himalayas, and this is in the northeast, the India itself. Okay, so huge databases are available now. And now this is our, if you want to plot them as MR plot, say, okay, so magnitude versus distance plot, you can see in the initial days, we had data from Cosmos actually. So this was one of the earliest network which has been put up in the India in the olden days, and it has recorded Dharmashala earthquake 1982, 1988. They were analog instruments. Okay, so this data was recorded long back, but now in the recent PESMOS has come. So you can see these are blue triangles. So these are all the recent data sets. So in the olden days, we had only this green, the inverted triangles here. So this was the olden days actually. Data was very few, but now after this PESMOS, so much of data has come. Now we have CIGN, Ganga network. There is a huge, instruments put up by NGR, right? So this also, lots of, they have recorded even the Nepal main shock, after shock, so much data sets are available. So now even in India, say, when I was doing during our PhD in 2005, we had very less data actually. To develop a GMP also, it was very difficult, but now, huge data sets. Now a lot of information is available, and then we can look at this data from, the artificial intelligence perspective itself. So this is a very interesting graph I'm showing you how the data has increased over the years itself. See, like for example, this is our Indian database. You can see here. So the Indian database, in the initial days, it was very, very few. And it's a cumulative value. So now you can see we have almost, it is also in the increasing stage itself. Japan, if you see, it's a huge actual. Okay, so you can see exponentially, it has grown. Now other places also, this is in the logarithmic scale. You can see all the records availability, they are increasing day by day. One earthquake occurs, you get huge data set. So now the question is, how do we understand this data? So how to understand the data? Okay. So ordinary conventional thing also, and then because the data is large, as already I told you, humans will not be able to detect actual. Only artificial intelligence will have a lot of superiority actual. Okay. So how to do these AI approaches on this data, or how to understand say these earthquakes, when the complex process which is linked to our earthquakes itself. Okay. So now this is what we said. So exponential growth in data has been observed here in all the regions here. So now how to, so, and earthquake is, we all know it is a very complex phenomenon itself. Okay. So now how to develop say complex relations, or how to understand any patterns. Okay. So there are any in the data, identifying patterns and other things, now patterns from the data. So this is a question, which we are asking actually. Okay. So generally what we do in our civil engineering or any things, as already I told you, the first step is conventional actually. Okay, we know our equations of motion, convention or finite element approaches. So we have also done this finite element approaches, whether we can model this data, say whatever data we have been recorded, whether they can be understood by the conventional method, that is essentially by finite element and other approaches also. So this is just the finite element model, for the Ganga basin, you see, which we have developed, Indo-Gangetic basin. Okay, so huge finite element mesh actual. Okay. So this is near the Delhi region, so this model we have developed long back, and it got published 2-3 years back. That paper is also available. So we developed this Ganga basin model, and this is the one which is recently to understand the Nepal earthquakes. Okay, so we did this huge the finite element model to simulate this earthquake, and then to know how good is this model, or how much we can explain the data with this type of finite element models itself. And you can see these finite element models, they are huge actually, 1.16 billion degrees of freedom. And you can run these type of complicated things, say only on supercomputers, not on your desktop and others. And finally, after doing lot of exercise, say, so our observation was, we can explain only the data we'll have from 0 to, so the data, if you see, it has frequencies from 0 to 50 hertz. But most of the energy will be from 0 to 25 hertz only. Okay. So the whatever the computational model, whatever we have developed, say, the issue is we can simulate only up to low frequencies only. So we can explain the data only from 0 to 1 hertz only through this huge computational model. So from 1 to 25 hertz, these models cannot, simulate the ground motion. Or these, although these models are very sophisticated models. So with these models, whatever I'm showing you, these are like, the state of the art actually. Okay. So right now, whatever things are there, so the best things if you try to do also. So these best conventional models, which you can say, so where you can model topography, all those things also. But still, the thing is, you can't go more than the 1 hertz itself. Okay, so that is a problem with these conventional, the finite element and other models itself. So you can see the comparisons up to 1 hertz, you will get a good comparison. But more than 1 hertz to 25 hertz, the comparison becomes worse, and you can't explain the data itself actually. The phases, the arrival times, it is very difficult to explain through this state of the art sophisticated model itself. Okay. So of course, these are all the three components I'm showing. So this I'm showing for the Nepal. So now, if you try to understand, so why these, the state of the art, the computational models are unable to explain, this high frequency ground motion, that is basically that is linked to the earthquake, the entire process of earthquakes. As already I told you, these earthquakes are very complex actually. So it is basically a complex process. How an earthquake occurs is still we don't know. It's extremely complicated. So the source, we have the source terms are there. Then the medium say. So in the medium, you can have like IG basin. Lot of geological layers will be there. Basin amplification will be there. Topography, this will be there, and then the site amplification say. So many things are there. Okay, and all of them will have uncertainties also. Okay, so that's where the things becomes extremely complex actually. So you may have, you may have the computational thing, you can develop a computational model like this to simulate ground motion. You can do all the hi-fi kind of stuff also, but still you cannot simulate ground motion more than 1 hertz actually. So that is the current situation in our earthquake engineering. Okay, so the mechanistic models are there, but none of them can simulate more than 1 hertz. So this is the thing. So now that's where, so these earthquakes are so complex actually. You can develop so the conventional methods, they fail basically, in simulating the ground motions more than 1 hertz. The reason for this is very straightforward actually. Now these earthquakes are basically, a multi-scale phenomenon we say. So a lot of scales are involved. You follow the time scale as well as the spatial scale also. Yeah. See, like for example, say, so this red line is the fault actual, okay, which you can see here. And generally what happens in earthquake is, you have the earthquake means the fault starts moving actually. So can any one of you can tell me what is the speed of an earthquake? What is the rupture speed? How much fast the faults moves at during an earthquake?
2 to 3 kilometers per
2 to 3 kilometers. Okay, so you just imagine, I have mentioned here also, it is something like 3 kilometers per second. You just imagine, your bullet train speed or whatever, your bike speed 60 kilometers per hour we travel, but earthquakes means extremely fast actually, 2 to 3 kilometers per second only. So what happens when things moves very fast? No. So when things are moving at that much fast, say 3 kilometers per second, so what happens, No. And this speed is more than the shear wave velocity of the medium, or it may be more than sometimes it is every material has a shear wave velocity, which we write as root of mu by rho, the material actual. Okay, so now earthquake speed, sometimes what happens is it is a close to shear wave velocity, or it may be more than the shear wave velocity actually. So now what happens if the rupture speed is more or less close to the shear wave velocity of the medium, say, now what happens now? Or if it is moving slowly, say, suppose if earthquakes are moving at 3 kilometers per hour, you followed, very slow, say, then what happens? What is the result of this high speed? See, when things moves very fast, what happens? Fast means you compare this with the shear wave velocity of the material. Okay, so all of you know, right? For bedrock, what's the shear wave velocity? Any idea? Rocks, how much shear wave velocity rocks have?
800 to 100,000 kilometers per second.
Very good. 800 to 1000 kilometer per second. Okay. Now, what is the rupture speed of an earthquake? So you are saying 800 to 1000, I think, right? Meter per second, I think. So if you write it in meter, it is 0.8 to 1 kilometer per second, you can say. Now, earthquake speed is 3000 kilometer per second actually. Now what happens? So now you tell me. So now your rupture speed is more than the the shear wave velocity of rocks itself. Now what happens? Or if it is less than this one, say what happens? More than that one, what happens actually? So this is a very important fundamental thing you have to understand in earthquakes actually. Now, any one of you have an idea? No. See, all of you are there, right? So what happens, you see? What happens in when your things are so fast? Just guess, nothing to worry actually. Okay, so there's not any serious thing is there. Just you can guess it.
System will be in shock.
System will shock. Okay, very good. It goes to shock actually. Very nice. So what happens? You followed it when it is in shock or something. So things starts vibrating actually. That is the main reason you followed it. Shock, and then finally things starts vibrating. Okay, so now this vibration only manifests at the surface you followed. So all the ground starts vibrating, and if you put up an instrument, say, if you record acceleration, it comes like this actually. And generally what we do is when things are moving so fast, say, you can compute displacements. Now in mechanics you have studied when things are moving so fast, you compute its derivatives actually. Okay, so we compute velocity, we compute acceleration. So this is how the instrument looks like actually. Now, if you go in this place where fault is moving actually, so after the end of earthquake, you will see like a permanent crack or something. If you put up instrument, it shows like this actually. The displacement will be something like this. So this component, we call it as a fling, or the permanent ground residual displacement also we call. Okay. Now, so the reason here is that the rupture speed is extremely fast compared to the shear wave velocity of the rocks and other things. So that is why the vibration comes actually. Suppose if the rupture speed was very, very small, say, then what will happen? No. So you have to really worry about earthquakes. Let us say the rupture speed is 3 kilometer per hour now, okay? Or 3 meter per second or something like that, say. And now whether you have to worry when rupture speed is very, very small, so what happens? See, when rupture speed is very small, say, we have whether medium will vibrate. No, it will not vibrate. So then if the medium is not vibrating, so then you don't need to do earthquake design at all. You can close this thing itself. Okay. So this is the most important thing. You can see the speed, how much, the speed things are moving. So these, and of course, the total vibration is only 100 seconds, or that is where, so that's what I'm trying to say. So this is a very, very complex phenomenon actual. And then what will be the length of the faults? See how much width will get ruptured. Generally, some of you would have seen, right? What is the length and width of the faults generally? Suppose if it is a 6 magnitude or 7 magnitude earthquake, say, any of you have an idea how much, the region, the rupture will be? You can guess, there is nothing wrong.
Hundreds of kilometers.
How much?
Hundreds of kilometers.
Hundreds of kilometers actual. Okay, so 7 means 150 kilometer like that. Now, what are the dimensions of our structure? See, our structural dimensions are now fault dimensions are in kilometers actual. Okay, so faults are of hundreds of kilometers. But what about our structure? Suppose it's in meters actually. So now what is the problem here? You can see the problem here. So earthquake means 100 kilometers. But then your structure is a few meters. So you can see the huge scale problem. You have to model a thing which is of hundreds of kilometers, and finally you have to, you understand, you have to design a structure which is very, very small, and the instrument is also located at very, very small place. So there is a huge spatial scales are involved. From kilometers to meter level you have to come. And then what is the lifetime of a structure? Generally apartments in our IS code, what is the lifetime of a building, or what do this
50
comment
years.
on that?
50 years.
50 years. But earthquake, how much time, if we're 7 magnitude earthquakes, what will be the duration of that earthquake?
Few seconds.
A few seconds. So now earthquake, if you have a Nepal earthquake, a large earthquake, it will occur for a few seconds, but this ground motion of this, you have to link it to 50-year time period. Actually, you follow the lifetime of a structure. So you understand the time scales, whatever we are looking for. So large earthquake, large dimensions spatially, but temporal, it is very small. If you take a structure, say, dimensions of our structure are very small in spatial domain, but lifetime is 50 years actually. So now, this is like a multiple time scales are there, so that is why this problem is extremely complex actually. And to add the complexities, if you have soil information, say the soil, right, how much soil is important. We take in our calculations, the site amplitude, in the ground response analysis you will study. So how much soil influences your structure? How much depth? 30-meter depth actually. And now you see your fault is having hundreds of kilometers, but finally you are saying a 30-meter soil will amplify, you follow, right? That is also another complexity actually. So you have hundreds of kilometers, soil is a 30 meter, then structure is a few meter. So and then in it spatially also, the time scale, these scales are variety scales are there. Even in time also, say earthquake will occur only a few seconds, but lifetime of a structure is 50 years. So, you have to link this extremely complex phenomenon. That's why, you can develop a sophisticated mechanics based model also, but still it will not be able to explain the data itself. So that is the thing why we are unable to explain this earthquake itself. Okay. So that's why what we do in practice, what one does is, that nobody uses this mechanics based models actually. Okay. In practical design, they directly work with the data. So we directly take the data actually. Okay. So we take the past earthquake data, say all the past recorded data. Yeah. And then what one does is, just take the recorded data, you develop some type of equations actually. Okay. So log y. So now in our design, say what is that we want? So if you know magnitude of an earthquake, you can't do the design. So if you want to design a building, so what information we require? No. What are the quantities we require? So in seismic design, say what is that you require? If I want to design a building, what is you require for earthquake?
Ground motion parameters.
What are those ground motion parameters?
PGA, spectral acceleration.
So response spectra, these things are required for you. Okay, without that you can't do the design. So what people have done in the practice is we have lots of data. So you find out PGA, you find out response spectra from the data, and then you develop this type of equation actually. So log PGA is equal to, some C1 plus C2M, like a simple equations they have built up actually. Okay. Now this was one of the earliest equations in 1970 or 1980, say, when data was very small. So they used to have just a few data, hundreds of data, 100 data or 200 data was there. So what people did was they simply fitted these type of equations also. Now what has happened in the last 20-30 years, huge data came. So people started observing that these simple forms, say they are not sufficient actually. Okay. They are not sufficient, and if you develop these type of simple equations, the data will show a lot of scatter, lot of error is there. So people, what they did was they tried to expand these equations actually. So they added all complicated terms, m to the power of 4, then fault mechanism, hanging wall, site amplification, like this. People have started adding so many things to the regression equations. Okay. So this is one of the recent equation, I think NGIS. You can see how complicated is this equation actually. So you have magnitude, distance, magnitude, then only magnitude, then this is a reverse faulting, normal faulting, then some C times RJB, ZR, regional, this, and these are extremely huge, complicated functional forms. Even when you look at their papers, the functional form itself will go to 2 to 3 pages actually. And then, the unknowns, if you try to find out these unknowns, is a A1, A2, A5, A4, all the constants, if you take, almost 400 to 800 constants are required to explain the data, and the error also. So when although your functional form is complex, but when you fit the standard deviation say of the error, so this is also very extremely high actual. Although you fit such a complicated model also, you are getting a extremely high standard deviation. And if you fit a simple functional form set, then this sigma epsilon will be extremely high actual. So after you fit a complicated functional form, the sigma decreases, but still it is extremely high. And then the number of constants are also 800, 400 constants, and very difficult to understand, these equations itself. Okay, so that is, so the reason is, so that is why in the recent 2 to 3 years, people have started looking for, these type of problems actual. So they based on, machine learning. So the question is, whether this huge database can I explain with less number of unknowns and with less standard deviation. So that is a question. Okay, so if we write here now, so can we model the data? Okay, with less unknowns, with low unknowns, now they are fitting 400 to 800, maybe somewhere around 100 unknowns are there, say. And then standard deviation also should be less error actually. So this is a question, we are asking actually. Okay, so whatever data is there, say, so can I fix a model this data with less number of unknowns? Okay, less than the conventional things itself. Yeah, and less standard deviation. So this is a question we are asking actually. Okay, so then this model will be a hit, or you can use these models and confidence level will increase actually. Okay. Yeah. And of course, this also I showed you, these models, these simple although these models are highly complicated, when you compare with the data, still there are problems actual. So whenever there is a topography or whatever, say, so these GMPs are very simple, but they underestimate actual. They cannot capture all these, although the functional form is highly complex, but still they are unable to explain a lot of scattering is there. You can see. See, this is a famous equation. You see that NJ West equation. You can see one line. You can see how much scatter is there. Say, like for example, at 200 kilometers, say, this line gives you this value actual. Okay, the PGV is it tells you 3 centimeter per second. But if you see the scatter here, huge error actually. You followed. So that same distance, you can get as high as 9 centimeter per second to 1 centimeter per second actually. So you can see a huge scatter is there, although the functional form is complex itself. And then if you see this equation, say CY equation or whatever, so this equation also you can see, although this equation gives higher values, you see the scatter here, how much will be the scatter when you compare with the data, say, it's extremely high. That's why the sigmas are also very high with this simple, the ground motion so-called, you see, these equations also. So now that is where, this machine learning has come. So the machine learning, the why we are using learning here is, so this is a question as already I asked you. So the question is, this is a question we are asking. Can we model the data, okay, with low unknowns or with less number of unknowns, okay, around 100 or less than these conventional things, and the less error actual. So that means we are superior to the these type of conventional forms. That is what we have to prove. Okay. So now, so that is where the machine learning comes into picture actually. So this is just a slide, I'm just showing you the brief thing about machine learning. So in machine learning, say, there are so many aspects are there. Okay, it is not just a simple subject. It is like a ocean actually. So you can have supervised learning, unsupervised learning. So supervised means you have objective function, you do optimization, that is essentially regression, classification. This comes then unsupervised learning. Say, we will discuss that in our the afternoon session. That is a dimensionality reduction, clustering also, groups. This method is the widely used actually. Okay, these networks are used. I will show you also. So that we will be discussing in our afternoon the session itself. So the supervised learning, say, so this we will discuss right now. So these are two branches actually in machine learning. Okay, and then you can use it for regression analysis, you can classification, clustering, dimension, so many applications are there. Now in all machine learning, so these are the steps actually. You can see here. The first step, that you have to find the performance criteria or, the prediction, this one. Then you have to take the data, that is the pre-processing of the data. Then you have to find out the inputs actual. What are the inputs? You have to use the model architecture actual. How many neurons and other things also. Then the stopping criteria actual, where to stop, and you should know once you have started, so where to stop, because you cannot make the error zero. So somewhere you have to have a compromise actual. And then optimization, what type of algorithm you are going to use, how you are going to get the weights, whether you will capture the local minima or the global minima. So all these are the standard steps actual. So take the data, process the data, what are the inputs, outputs you have to do, then the model architecture you have to do, stopping criteria, and then you run the optimization, and then you find out, say, whether it is good or bad, or you will have certain step of parameters itself. Okay, these are the general basic steps in machine learning, which I think most of you maybe know. This, of course, these things are standard even for regression analysis also. Say, when you have the data, if you want to fit a straight line also, you find out what is x, what is y, then you fit it, and then the least squares regression you do. So same steps here also. It is just a non-linear regression only. Okay. And now in machine learning, say, so basically this machine learning is, they are universal approximators, they say. So theoretically, you can mimic any function actually. You followed. So that's what they say. They are universal approximators. So any complex problem, say, in theoretically, whether practice it is a feasible or not, that's a different question. But in the theory, you can approximate anything actually as per the definition. They are using this machine learning. Then they are most suited for non-linear, the complex behavior if you have, or non-linearity if you have. So these machine learning will work perfect for this type of problems also. And then when you are, as already I told you, when you are having huge data, say 100 terabytes or this one, machine learning works much better actually. You followed the shallow, this human eyes will not be able to handle. But machine learning works very extremely good when you have huge data, that is identifying the patterns and other issues also. Then of course they excel with large data. So in machine learning, say, the main starting point is you should have a large database. Okay, small database if you have, then these techniques, they have some problems. But if you have a large data, they work perfect actually. These machine learning techniques, and of course they can handle even images also. I will show you some examples also. If you give an image also, they can take it as a inputs in that RGB, red, green, some thing like that, and they can even classify also which is what and other things also. So these are some of the advantages or the capabilities of our machine learning. Okay, so now in machine learning, so a lot of networks are available. So I will just show you some few of one of them. So this is the one which you call as a shallow neural network, the simple network actually. Okay, so there is a simple. Most of you, I don't know how many are working in ANN or whatever. In 1980s, in the olden days, 1980, 1990, several papers was published, to to find out compressive strength of a concrete, or to find out the area of steel in the RCC beam, given the loads or whatever the area, all those things were there, or forecasting something, rainfall, predicting something. So people used these type of networks. So these are known as a shallow neural network actually. Shallow means only one hidden layer. Okay, so with only one hidden layer itself, they used to explain, lot of papers got published. So now the terminology is, so these type of networks we call as shallow. So shallow means only one hidden layer. That is the terminology right now we use. Then we have what we call as a deep neural network actually. Okay, so deep neural network means you will be having several hidden layers, 1, 2, so many hidden layers will be there. Okay, and then unknowns also will be high. So unknowns are extremely high because neurons are more. So obviously the weights and biases will be extremely high. But if it's a shallow networks, unknowns are small, but it's a very simple and it can be used for simple problems itself. Okay, and then now auto encoders also are there. So these also one more deep neural network only they call them. We call them as auto encoders. So they are widely used for dimensional reductionality. So to reduce the dimensions, say. Okay. So we use these type of networks, okay, and they have large amount of unknowns also, and so a large amount of unknowns means a large amount of data is also required here. Yeah. Apart from that, so this is one more network actually, LSTM they say, that is a long short term memory. So if your data has some type of a patterns, say, okay, like in our Fourier amplitude spectra, response spectra, or even the time history, like for example, the data is, has a correlations actually, okay, so that is they are linked among one another, say. So then we use these type of long short-term memory kind of networks actually, okay, where the memory in the data also is incorporated in the model, and this network is so powerful. It also tells you, say, how much is this memory of your network, how well they are correlated among themselves. So that also can be captured by this LSTM network also. And nowadays, this is another network, Bayesian neural network. It is same as your shallow neural network or deep neural network. But here, the weights, say, the unknowns are treated as random variables actually. So the unknowns, say, okay, so we treat them as random variables. So we don't find out the unknowns. We will find out the probability density function actually of the unknowns. And these are a stochastic neural network. Okay, so because they are random variables, every time you give a input, you will get different outputs. You will get a probability density function itself. So these also one type of network is there. Then we have another one which we call as convolution neural network also. So this network is widely used for images actually, slip images. You can detect this one. So I will show you some applications of these networks also. So in today's sessions, in the morning session, I will be talking now in this lecture and 12 this one. So we will be focusing on the shallow neural network actually. In my afternoon lectures, I will show you deep neural network, autoencoders, LSTM. We will discuss some brief this one. Then right now and I will also show you one more network, general adversive networks actually, GAN. These are the words which we use. So some of the very advanced things we will discuss in the afternoon session itself. Okay. And now coming to this new definition of neurons. Okay, what do you mean by neuron? The mathematical definition. So people say brain and other things, okay, that biological things anyway, I will not go into details. So this was the first neuron, or the first concept, say, of neuron, which we know as McCullough-Pitts model actually. It was developed in 1943. Okay, one of the earliest neural network actually. So this was developed, I think, in electrical or some other discipline. What the specialty of this network is, so this is a neuron, say, okay, so this is our neuron actually. So what it does is it takes, these are the inputs x1, x2, x3, x4, x5, and these are the weights actually. So you multiply, so this will be W1 into x1, W2 into x2, W3 into x3, W4 into x5, W5 into x5. So you multiply by all these weights, say, that is this multiplication, and you add some bias or whatever here, and this output is this is like a step function actually. So this is a neuron. So the neuron is like a step function. And you know the step function, right? H of z, if you h of t. So the step function is like these are a step function we have plotted here. Okay. So if it is a less than 0, say, the value is 0 actually. If it is more than this one, it will give 1 actually. Okay. So this is a simple neuron actually, okay, which was used in the long back. So its output is 0 or 1. So once you give the inputs, it multiplies by the weights. And then, if it is more than, the 1, it gives, so if it is more than some 0, say, it gives 1. If it is less than 0, say, it gives 0 itself. So this was a, very, preliminary, or the one of the earliest, the neuron developed in 1943 in the very olden, the days itself. So very, very simple neuron, just output was 0 or 1. This way or this way actually, like that it was developed in olden days. Then after that, this is a concept of perceptron came into picture actually. Okay, so this is a perceptron. So the neuron, they have improvised this one, and this has been done by, I think, Rosenblatt or somebody, I think in 1958, 1962, say. So instead of 0 and 1, they started saying that, it should be able to give any value also between 0 to 1 or minus 1 to 1 or something like that. So this model also contains, this several neurons actually. So you can have, several, these are the inputs here. And these are the neurons, output neurons or whatever. So here also you have weights actually, W1, W2, W3 like that. So what it does is here also it multiplies by the weights actual. And of course you add some constant like a threshold or something. Now instead of step functions, say, they used this type of sigmoidal functions or tan hyperbolic functions. Step function means it can give only 0 and 1 only. Okay. So this side or this side, it can be used for classification actually, whether it is whether it's a cat, something, classification. But now this perceptron means it gives you output also, continuous function kind of a thing. It came up. So this is what the sigmoidal function, which they use in perceptron itself. So now once this perceptron concept came into picture, say, then this whole subject of artificial neural network, everything got, motivated, and then people started using for prediction and all other type of problems itself. So now, so the keywords to say in machine learning is, we use these words actually, learning, training. Okay, you should know these things, the definition. So learning or training means detecting the data patterns. Okay, so this is what, so we are designing a network to learn something. That means what is a pattern in the data. So we are asking the network to learn these patterns in the data itself. Okay. And of course, predictions also can be made actually. And now network said that the definition of network means it is based on architecture between inputs and outputs actual. Okay, so this is a typical neural network. So like this is what we call as the network actual. So network means the architecture. So what are the input neurons, how many hidden layers are there, and how many hidden neurons are there. So like that we do all these calculate. So this is how a typical neural network looks like. So if it is one hidden layer means a shallow network, 2 or 3 or more than that, say, that comes to deep neural network itself. These are some of the key. Now we will say network parameters actual. So what are the network parameters? If you see the weights and biases actual. So the weights means these expressions. Okay, the connection. So this is nothing but a weight, well, W1, W2, W3, W4 like that. And of course, at each neurons, it has a bias. Bias is nothing but a threshold actual. So if you want, you can make bias 0 also. Generally, you estimate biases also from the data itself. Okay. So these are the network parameters, weights and biases. So whenever you are doing a neural network, so generally the neural network definition is we find out weights and biases. So it is just like a regression equation only, nonlinear regression. The unknowns are weights and biases in your network itself. So these things we will find out during the training process. And then we also call as hyperparameters actually. Just note down these important words. The hyperparameter means these are like additional parameters. We don't learn actually, we fix. So before the training actual, okay. So these are some parameters which we have to fix it. I will tell you what are these hyperparameters. Okay. So training set say, and then we have having training set also. That means the data which is used to train the network. We will not use the complete data. So it influences what the network learns also. So generally, if you are having a data set, 70% should be used for training the data. Actually, your network training means you are estimating weights and biases. So we estimate weights and biases in our network actually. So this is what we call as the training set actually. Then other one is a validation set actually. Okay, oh, sorry. Now other one is validation actually. Okay. So validation means you have to assess the network generally. See how, because weights and biases you are finding from the 70% of the data set. So some 15% of the data you have to validate how good is your network or something. So performance during the training, and it mildly influences the network training because weights and biases are found out only from the 70% of the data. Then we have a testing set also. So to test the network performances after training, so after you have found out everything, we test how good is the network also. So it needs to, this is like a real, the check itself actually, okay, and 15%. So you can see, so whenever you have data sets, so 70% you use for training, 15% for validation, then the remaining 15% for the testing data set. So the 100 data you are having, so 70, 15, 15 you have to use actually. So this is a standard practice actually. And why 70, why 15, why not something else? So this comes from experience. So you can try, like you can take 80, 10, 10 or 90, 5, 5 or even 50, 25, 25. So that you can decide, but this is a generally acceptable, the practice in machine learning. Now, objective functions say. So the objective function, sometimes they also known as a cost function or whatever. So it is just your least squares error actually. Okay, the same whatever least squares you know, right? So this is observed data. So this is a recorded data. And this is the ANN data, predicted actually. So which is predicted from the network actual. Okay. So this error we find out and we square it. So it is what we call as least squares regression actual. Or sometimes mathematically we call this as L2 norm. Now, sometimes what happens is in practice, if you want high frequency things are there, say, we use L1 norm also. So that means instead of squaring the data, we take absolute value. Okay, so this is mean absolute error, they say. And this is mean square error. Okay, so we decide L1 norm or absolute you want to use or MSE. So if the high frequencies are high data, high frequencies, we use this thing. And if it is a smooth, say, we use this norm. So generally, most of us use MSE only. Nobody uses MAE, but there are specific problems are there, so where you may have to use a MAE also. Okay, so this is what we call as objective function. And now this is how the network class. So these are the inputs. So these are input layer actually. Okay, and M are the number of, let us say, the input neurons, say. So these are shallow neural network. So there is only one hidden layer. And let us say N are the number of neurons in the hidden layer. Yeah. And output layer has a K, say. So K is number of output neurons. Now, so now what we do is Hj. So this neurons Hj, this is equal to, so these are the weights W1, W2, W3 or something. So inputs are X1, X2, X3, say. So we do W into X plus we also add bias actually. So these are threshold. So this also we find from the database itself actually. So now at each neurons I have a bias. Okay, so B1, so Bj, like that, you see we have this one. So now this is a Hj. So this is the output at Hj, Hj is this one. Now this is output Yk, say. So Yk comes from Hj's only. So here also we have a weights. Okay, so that is from the hidden layer to this one, and we also have a bias actually. So this also contains bias. Okay, the output layer also. Yeah. So now what we try. So this is our network. So you can write like the Hj, Yj. So now this is our objective function. So what is that we have used? L1 norm or L2 norm? MSE we have used or MAE? Can you see this and tell me? It is a mean square error or mean absolute error? See, all of you are there, right? So now you see this one and tell me what is this error? No. Me MSE or MAE? What is that you are optimizing? See, we have taken absolute or we have taken square? See, all of you are there? No.
Absolute, sir.
No, see here carefully. What is that here? See, now you have squared or absolute we have taken. See, Yk is anyway your data. Okay, so this is your data. No. This is predicted from the network actual. Okay. Now what is that we have done? So this minus this will give you epsilon. We have done here. What is that we have done here? No. We have squared it actually. So when you square it, say what is that error? No. See, once you have squared, say this is what you have read. So what is that error? Mean square or mean absolute? No. Tell me.
Mean square, sir.
It is a mean square error. Okay, so now right now what you have done is MSE. But as already I told you, you can take a square or you can go for absolute also. It depends on the problem, but most cases we will do least squares only. Okay, it depends. And now you can see M is the number of input neurons, N is the number of hidden neurons, K is the number of output neurons. Now you can easily calculate how many unknowns are there. It's a very, very important thing in neural networks. Okay. So now what are the unknowns here? Weights and biases actual. So now how many weights are there from input layer to hidden layer? So for inputs are M neurons are there, hidden neurons are N. All of them are interconnected actually. This hidden is connected to this every. How many unknowns, how many weights are there from input to hidden? M is this one, N is this one. How many weights are there? Or see in this problem, there are three are there here. So three input, 1, 2, 3, 4, 4 hidden neurons are there. So in this range, say what is your, how many unknowns are there in this region? How many weights are there? 3 and 4. How many weights are there? You can count the lines and you can tell me. Only from input to hidden. Just guess, guesser, you can easily calculate it. How many lines are there from input to hidden only? 3 and 4 are there in the graph which I am showing you. Okay, so how many weights are there? You can calculate the lines. So this is 1, 2, 3, 4. So this neuron is connected to, the input is connected to all 4 actually. 1, 2, 3, and then the 4 actual. Okay, so these are 4 are there. Now for this also, excellent. I think Surabhi, somebody told 12, fantastic actual. So 3 into 4, that's all on. That is what we say M into N actual. Okay. And now from hidden to outputs, how many unknowns are there? Tell me in this graph, tell me now 3 hidden are there, sorry, 4 hidden are there and 2 outputs are there. How many unknown, how many weights are there? So just see the line also. Line you can count and or you can tell me the simple thing. Now the logic I told you, right? 3 into 4, 12. Now this is a 4 into, this is how many outputs are there? So total how many? You can type in the chat box also. I think somebody is typing, right? 8 Saloni Pandey. Okay, very good. 8 here, the unknowns here. So now in this network, whichever I have shown, so that is what we write as M into N plus N into K actual. Okay, so that is how we write these number, that many weights. Now apart from that, so we also have bias actual. So bias for each neuron, you have a 1 bias. So 4 hidden neurons say. That means 4 biases are there. Even outputs also will have bias. 2 are there, so 2 biases. So that's what we write as M plus K biases actual. Okay. And now you tell me in this network, whichever I have shown here, how many total unknowns are there? So in this entire network set, tell me how many unknowns are there, including biases. Tell me how many total unknowns are there in this network, which I am showing here. You can use this formula also. Tell me how many unknowns are there. You can type in the chat box also or whatever. So 3, no 10, no total number of unknowns in the network. So 3, 3 inputs, 4 here and 2 here. Total number of weights and biases. You can use this formula also I've given here below. You followed. You can type whoever type. 25 Saloni. So how did you get that 25? So 3 into 4, 12. Then here 4 into 2, 8. So 12 plus 8 you have. Plus you are having bias also. 1, 2, 3, 4. 4 bias here, 2 bias here, 6 actually. So how much it comes? So 3 4s are 12 plus 4 2s are 8 actual. Plus biases are 6 biases are there. So how many now? Surabhi says 22. Be careful here. So use this formula. M is 3, N is 4, and K is 2. Let me write also. M is 3, N is 4, and K is 2. and use this formula here. Now you can see here. So m star n will be 12, n star k will be 8, m plus k is 4 plus 2, that is 6 actually. So now total how many? 26 actually. Very good. Okay. So this is how. Okay. So Rabi, okay. I think she made a calculation mistake. Perfect actual. So total there are 26 unknowns actual. Okay. So generally whenever you are having that, this is a very, very important. Okay. So let us say you are having 100 data points and you want to fit for 100 data say. So your number of unknowns should be always less than number of samples. This is the most important thing. Suppose you are having 100 data points say. You have designed a network, and unknowns are also, 150 unknowns are there. Say. It looks ridiculous actual. You cannot find out, from 100 data, 150 unknowns, it is something, you're having 2 points, say, and you fit a cubic polynomial or whatever, it's not possible actually. So generally, the number of unknowns should be less than the number of samples, and the thumb rule is it should be number of samples divided by 2. So if you are having 100 data points, say, so your number of unknowns in network should be less than 50 actual. So that is the thumb rule we use. So this you have to use actual, okay, to find out the number of unknowns in the network. So if you do more number of unknowns, say, then you will be trapped into overfitting, and you will have a lot of other problems also. So you have to be very careful actually. Now after you have, so this is how you design the network. So you find out how many inputs, how many hidden layers you want to take, how this one, and you start your network say. Now you have to find out the weights actual. So these weights we use lot of optimization algorithms are there. Okay. So Levenberg market algorithm, LM algorithm, then the steep descent gradient algorithms. Even these are all local, and even the genetic algorithms, simulated annealing. So many techniques are available right now, and no need to worry about this because MATLAB has inbuilt toolbox. It does, So you try to find out the objective function, that is this J. So this what we do is you have to do Taylor series expansion. You have to find out derivative of your objective functions with respect to weights in the Hessian matrix. All those things you have to do, and then what initially you start with some weights, and then you update say in each iteration kind of thing until it converges. Say like for example, you start here say, so this is a method Levenberg market it or whatever. So it goes like this, like this, like this, like this, and finally you approach a minima, or sometimes you can go like this. So variety techniques and methods are available in the literature. Okay, so you can use any of these methods, and none of you no need to worry if you don't know these optimization techniques. Also, it is fine. MATLAB and others have inbuilt toolbox actually. Okay, no need to worry about this at all. Okay, so this is one. So now the first thing is you initialize the weights at adequate values. So first you identify your input outputs that anyway you decided. Okay, so now you assume some weights say. So now you take the input from the training data. So you assume that this itself as a final weights. You find out the error say. So once you have the error, you calculate the derivative of the weights, based on this Taylor series expansion and other things also. And then you correct your weights actually, delta W ij, it may be negative or it may be positive. So it goes all the ways around, and then you repeat these steps actually, iterative, because it is non-linear, So you have to do like this step I told. First step, you start here, say, you go to here, okay. Then once again you do, then once again you go here, once again you do like that, iterative. You have to do the things itself. And finally, error will not be anyway 0. But error will have some acceptable tolerance levels. You stop your network itself. Okay, very simple. And these are the challenges actually when you do a network say. So you can have your objective function will have several minimas actually. Okay. So now if you see this figure say, which is the correct minima. So these are objective function. We have 1, 2, 3, 4, 5, which is the correct minima where this function say, which is the correct minima here. We should go up to which point actually, 1 or 2 or 3 or 4 or 5. Just tell me if you see this figure, say where is the minima located at which point? At 1 or 2 or 3 or 4 or 5. Which is the one best minima? 3. Excellent actual. So But generally what happens in our algorithm, these gradient methods, no, suppose you start at this point, say, what happens, your algorithm, it goes to 1 only actually. So it will be trapped in the local minima. It will not go to 3. You followed. Suppose if you start at here, say, then directly you may go to 3. But generally we don't know. Suppose if you start at this place, it may be trapped in 5 also. So this problem happens in practicing, you know. So the local minima, say. So if your objective function has several local minima, then your algorithm will have problems actually. So to handle this problem, we do global, you know, the minimas are global optimization algorithms are there, like genetic algorithm, okay, simulated annealing, then a neighborhood algorithm. So these are some of the algorithms actually, which you have to use if your function has so many minima. This is one challenge actually when you do this training here. And other one is overfitting actually. So you can see, so the same database, how this function has fitted, you are having a neural network, you can see how it has fitted to all these, what we call as, you know, overfitting actually. So it will have so many oscillations, but whereas this is like the best fit kind of thing. You follow it. So this also has to be avoided. Sometimes, you know, your network may overfit or it may underfit the data also. So these are some of the challenges actually. So that's why we do training. I told you, right, 70%, 15%, 15%. So we divide and we find out error in all the 3 approaches actually. So, and we take a point. So training, you can see, as you increase the number of unknowns, the training error will automatically decrease actually. So that's why validation, if you do say that data which you have not used 15% of the data. So now you identify the point where, you know, both of them will be minima actually. Okay. So training means minima may happen at some other time also, but you have to take validation epochs, this one, such that you will not be trapped in local minima as well as the overfitting of our, you know, the curve itself. So this is what you have to be very careful. Okay. Now these are the keywords I already told you. Now the first thing is, you know, the normalization generally. So these are very important in neural networks. All the inputs, we normalize them to 0 to 1 or 1 to +1 actually. Okay. Why? The reason is, you know, so like for example, magnitude is 1 input, say. Okay. This is magnitude and this is a distance actually. Generally, what is the highest magnitude? Magnitude will range from what number to what number? Can anybody tell me? Generally, a earthquake magnitudes, say, they lie between which range to which range? See, magnitude of earthquakes, say, they lie from where to where? What is the typical magnitudes? We observe. You can type in the chat box also. What is the you know, magnitudes we generally observe? So I showed you, right, this database also. So when you look at this database, see, I have shown you, I think, in the previous slides. Okay. Now you can see this graph actually. Okay. And now you tell me what is the magnitude scale here? What are the typical magnitude ranges in the y-axis? Can you observe? Magnitudes are going from where to where? All the data. 3 to 8 actually. Excellent. Okay. So your magnitudes are from 3 to 8. Now when you look at the x-axis, distances, they go from where to what kilometer? You can type in the chat box also. I think, you know, what is this? So magnitudes lie from 3 to 8, but whereas the distances, 0.1 to 100. Oh, okay, 100. This is 100 actually. 10 square is 100, but the data generally 200 kilometer, 300 kilometer, 400, 500, or it can go to even thousands also. Okay. So this is how, you know, the magnitude. So now this is also one more graph, say. So here magnitudes are going from where to where? You see this graph? This one, if you see, say. So magnitudes here, they go from, you know, 2 to 8 actual. But whereas if you see the distance, say it can go from 0.1 to 100 kilometer, it can go up to even 1000 also. See this graph, you have data up to 1000 or 2000 kilometers also. So this is a big problem, when you try to do the neural network, when you directly want to utilize the data actual. Okay. So that is why this training we do. So that's why the scaling is required. So magnitudes, they go from 2 to 8 actually. But whereas the distances, they go from 0.1 to 1000 kilometers. Okay. So the problem, what happens is when you try to do this, the weight, this expression, so that is, Wij into Xi plus Bi. Okay. So this expression, if you try to do, that's a Wij into Xi say. So what happens is when you try to do the data, so this weight will be there. Wij magnitude will be 8 only maximum. Plus you have to do Wij into 1000 kilometer also. Now what happens? Which will be higher? And the weights will go from -1 to 1 only. Okay. So when I try to add this entire thing, say, so 8 times W1 plus 1000 times W2, say, now which one will be dominating here? Suppose let us say weights are 0.5 we have got actually. So which is the one which dominates here? So 0.5 into 8 will be 4 plus 1000 into 0.5 will be 500. So which is the one which is a dominating thing? Distance only. Excellent. Okay. So that means, when you try to add something, say, because it's all adding only. So what some quantities are small, some quantities are very, very large actually. So what happens is the distance only influences your data, which is wrong actually. Okay. So to avoid these type of things, what to do is we do this normalization essentially. Okay. So we scale all these values such that all the inputs will have equal weightage. That is the main idea here. Okay. There's the idea we have to do when you run a neural network. Okay. So there are variety of scalings are available. So min max scaling actually. So what we do is you find out the minimum value. So minimum magnitude is 2, maximum is 8. You divide by 8 minus 2, that is 6 actually with the entire database itself. Now distance, if you see, say 0 to 1000 kilometers, so you divide all the distances by 1000 kilometers itself. Then everything will be lie from 0 to 1 or in that range itself. Such that so this also will be from 0 to 1, this also will be from 0 to 1. So all the inputs will have equal weightages, in our calculation. So there are several type of scalings are there. Z-score scaling like normal, standard normal, tan hyperbolic scaling. So these also mandatory. So when you have the data set and your data, each variable will have different variations. You scale all of them to the same 0 to 1 or maybe -1 to 1 scale before you start running the network actually. So these are some key points actually. Then underfitting, overfitting, as already I told you, if you do, more number of unknowns or if the number of unknowns are more than the number of samples are, more than half or whatever, then you will have overfitting actually. So this is what we say overfitting. You can see the network is not smooth and it goes something you followed, right? It tries to fit to the every data points. This happens. So the underfitting means if less number of unknowns are there, so it will have like this. This is the best actual. Okay. So this you have to identify. So this is a typical regression. Of course, the same thing in classification, deep learning, we will see. So this happens actually. So that's why that 70%, 15% we nicely verify actually. So that helps you to do this underfitting, overfitting and other things also. So overfitting means network is large, unknowns are there. So it learns noise also. So you have to reduce. If it is underfitting, say, so network is small, so you may have to increase the network size also. Okay. And hyperparameter, I already told you. These hyperparameters means we will not find out these hyperparameters. So these are like a tuning parameter, they say. So sometimes they say top level. That's how the artificial intelligence people textbooks they write this one. So they are not learned during the training, but they are the parameters which control actual. So one is the number of hidden layers. Okay. So how many hidden layers have to be there, say. That is in your hand, weights and biases that you decide. Weights and biases you find from the optimization. But how many hidden layers, that is you have to decide beforehand actual. And in neurons in each layer, so whether I have to go with 4 neurons or 5 neurons or 10 neurons, that is a hyperparameter. It is not learned during training. You have to do it separately. Then the learning rate is there, say how fast things are learning. drop rate, L1, L2, which we have to use. So they are all what we call as hyperparameters only. So these parameters have to be, tuned before the network itself. So there are several methods are there. One is grid search actually. Okay. So what they do is it is like a brute force technique. You assume one hidden layer, say, and you assume 4 hidden neurons. You run the network, you find out net weight, bias, and all other things, and you find out error. Then once again, you take a 2 hidden layer and you increase the number of neurons, and once again, you run the network, you find out error, say. So you plot all of them, variety of cases, and whichever is minimum, you take it actual. So that's what we call as is the grid search actual. Okay. Now other one is random search also. So like, you randomly like one hidden layer, 4 neurons, 2 hidden layer, some 3 neurons, something like that. You randomly do this one and you find out the point where things are minimum kind of thing you do. Then Bayesian search is also recently now it has become very, the popular. So Bayesian means whatever the previous information you use it and then you update actually. So like 4 neurons, you have already got the results say. So when you do for 6 neurons, you use the previous information, you update the errors also. So like that variety of methods are there, grid search, random search, Bayesian search. But nowadays what people do is mostly grid search in the olden days. But now the thing is Bayesian models are becoming very, very popular actually. So these are hyperparameters. So hyperparameter means number of hidden layers. Okay, and number of neurons, like hidden neurons actually. And learning rate, that how in the algorithm, optimization algorithms, how do we fix these numbers? So these are all what we call as, you see, the hyperparameters actually. Okay. So this is what we say. So hyperparameter tuning says. So we do number of hidden layers, so these are more important thing. So network, more number of layers means network complexity increases, more data, overfitting may happen. Then neurons in each layer, so these are hyperparameter actually. How many numbers? More neurons means more complicated this one, more data is required, chances overfitting also will happen. Then L1, L2 regularization also we do, like you can see here, error is there. So we have told you y minus y hat whole square, the mean square error. We also add the number of neurons are more, say, these extra terms also. So these quantities are known as smoothing actually. The smoothing parameters or whatever, or sometimes in optimization mathematical language, we also call them as Lagrange multipliers. Okay, this also we add in the data also. So this lambda 1, lambda 2 set. So these are all the hyperparameters actually. Okay, so that's what we call as L1, L2 regularization also. So this one then learning rate actually. So these in the optimization algorithm, the initial learning rate and dropout percentage. So these all have to be fixed before you do your neural network. So the challenge is how do we estimate this parameters itself is a big challenge. So you have to do trial and error, as I told you, random search, grid search, Bayesian search you have to do, and you have to fix these parameters also. Okay. So this is an example, the grid search example for hyperparameters. Okay. So you can see this is your error with I'm plotting with respect to the learning rate actual. So training error I have plotted, validation error I have plotted, testing error also we have plotted. So now if you see here, say, now I have plotted 1, 2, 3 here. Now can you comment what is 1? What is 1 basically? Can you identify perfect fit, underfit and overfitting? So I already told you training error means 70% of the data, validation 15 actual. Now what is happening in this range? Near 1, what is happening? This region, so what is happening? What is the error here? In this region, it is high or low? In all the 3 periods, training period, validation period, testing period, the error is high or low in the one that place. See, when the initial learning rate is 0.01, say this place actually, what is the error here? It is higher or lower here? You can type in the chat box also, you see. And in this region 2, so what is your comment actually? What is the error here in training, validation, testing period actually? Can you comment it? and your x-axis is hyperparameters. Higher error they are saying. So this means underfit actually. Now here in 2, region 2. Comment on region 2. So what is happening in region 2? In the region 2, what is happening here? It is low only. But what is the most? Now you see region 3. This region say 3. What is your comment? Now third one you tell me. 2 you have told it is low, but in 3 it is a medium or what? But no, but it is a medium. Here also it is low only. But here if you see here, what is the error in training? This line shows training actual. The blue one is a training period. Okay. This is validation is this one. Training testing is also here actually. What's the difference between training error and testing error and validation error? Here the difference between these 3 lines is when you compare 2 versus 3, say 2 and 3, of course error is low only, but in 2 what is happening? What's the difference in error in the training period, validation period, testing period, say? Which is better, 2 or 3? Both the cases error is low only, but the difference of error in training period, validation period, testing period, where it is high, where it is low actually. Which is best, 2 or 3? Two is lesser difference actually. Very good. 2 is best. So that means this is the perfect actually. You followed. So 2 is the perfect. So you want to have so these hyperparameters to say, if you want to tune, so what to do is you run the network, you find out error in all the 3. So all the 3 error is converging, say almost same. That is the perfect, the identification of a hyperparameter. So in the second case, third case, what is happening is error is low only. But training error is low, but the difference between these errors is so huge actual. So this indicates, overfitting basically. You followed. This is overfitting. This is the best optimal thing, but this is the underfitting actually. You followed. So this is how we tune our hyperparameters actually. Now here also, if you see this figure also L2 regularization say. So you can see here also it is like overfitting, kind of thing. Because training error is very low, but testing and validation is not low. You follow, right? There are a lot of differences out there. So these plots also one has to do to find out the hyperparameters. Okay. And now regarding the activation functions, say that McCullough-Pitts, they use the hit, that step function. Then slowly, as I told you, right, sigmoidal function, tan hyperbolic function. So variety of functions have come up actually. The real this function, leaky, many of them are used. So it depends. If the problem is nonlinear, say we use sigmoidal and tan hyperbolic. If the problem is linear or whatever, say we take some linear functions or whatever, we try to do this one. And all these functions are continuous and differentiable actually. So this is a very important, so that because to find out the weights, so we are differentiating the function. Okay. So because the derivative of these functions exist, we use these functions in our calculation. So generally non-linearity means sigmoidal function or tan hyperbolic function will be used in our calculations also. Okay. So fine. So I think 11:30. So Kalyan, you are there, right?
Sir, we will give half an hour break, sir, and at 12 o'clock we'll start the session, sir. You are muted, sir. Hello? Your voice is not coming, sir.
Now it is fine.
Yes, sir, yes, sir.
So we'll half an hour break. No, now I think we will take.
Okay, sir. At 12 o'clock we'll meet, sir, again.
Sure. Okay, fine.
Yeah, please carry on, sir.
All of them have come back, right? So anyway, so once again, you see, good afternoon to all of you. So I think morning session, I have introduced you why this artificial intelligence, machine learning is required in earthquake engineering. And then I have shown you, you see, what is the most important things in a neural network. Okay. So as already I told you, the most important thing is the number of the unknowns. Okay, so these where you have to have a very hold on the problem. So number of unknowns you can easily compute by number of inputs m into n plus n into k, plus you have to add the biases also. With each hidden layer, then the output layers, you have to add these biases. So you can easily calculate your number of unknowns, and they should be less than the number of samples by half actual. Okay, so this is a thing which you have to keep it in your mind. Okay. And then I also told you hyperparameters. So this, and of course, this is the most important thing, scaling actual. Okay, because one variable will be very large, one variable will be very small. So this also you have to handle. And finally say, so okay, the hyperparameters, you have to tune them, a lot of approaches are the grid search or Bayesian search. Say. So for that, you can use these type of graphs actual. Okay, that's 70%, 15%, 15%, So you plot, all of them should converge actually. Then only, you should take that value and then you develop your network. So these, the rules which we use to design the networks. Okay. And now finally, say, now the activation functions, as already I told you, if the problem is nonlinear, say, so we have sigmoid, tan, hyperbolic, those functions have to be used. If it is a linear problem, so you can use linear functions, and it is same as approve. Okay. Yeah. So you can use this type of the small this linear kind of issues itself. Okay, this is what we have said. Yeah. So you can sorry. So this you can use it actually. Okay, so now this is how the typical neural network works. This is just I have picked up something like this is a shallow network actually. Okay, the shallow network, you have this simple one hidden layer. So you can see, and these are the three inputs say, and this is your output. So this has been done for a concrete actually long back in one of the papers. I just picked it this network itself. So now can any of you tell me how many number of unknowns are there? So three inputs are there here. Okay. So three inputs are there. Yeah. And then hidden layer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 hidden are there. And one output layer is there. Can any of you tell me how many number of unknowns are there here? Using the same formula, say. How many weights and how many biases are there? Okay. So from input to hidden, how many are there? 51. Somebody has told. Plus into 1 biases actually. So 10 are here, 1 is here. So total 11 biases are there actually. Okay. So 51, the total number of unknowns. I think Surabhi somebody has answered, the correctly. Now this is what they say feed forward, the same thing only, which I already have explained. So you have a neurons, okay. So it takes all the inputs multiplied by the weights and you add a bias. It is just like a threshold actually. Okay. So if there is no bias, automatically your network will tell you B is 0 only. There is nothing to worry. So this is how a feed forward network goes. Okay. So these are the inputs, you multiply by the weights. These are the neurons. And finally you go to the output layer actually. Now the back propagation is nothing but your optimization algorithm. So you take the inputs, you multiply by these things and the sigmoidal function or whatever, you go to the output. Anyway, you have the recorded data, you find out the error and then you do the derivative and then you back propagates and then you update your weights actually. Okay. So this is what we try to do in the network. So now these are the algorithms, as already I told you, Levenberg, Marquardt algorithm, stochastic gradient, adaptive moment estimation. And nowadays, people are using genetic algorithm also because as already I told you, because we have issues with, the local minima, global minima say. So these algorithms are very strong, popular, to get this global minimas also. Okay. So now this is what we said, the learning rate is there, eta, how much is the learning rate? I told you it's a hyperparameter. So you have to find from that random search or grid search or, the Bayesian things itself. So you do this until your error is minimized or it is less than some epsilon actual. So now I'm just illustrating you with a simple example. I will show you the code also. So this is a steel beam, you see, ISMB 300, and it is simply supported actually. Okay. Now we want to find out the deflection. So this is a shear force diagram, this is a bending moment diagram. The deflection. So from analytical calculations, you already know this expression also. Now you want to generate a neural network, say. Okay, so now we develop a simple network actually. Input is load, that is a UDL, the per length this load. Then the Young's modulus we want to find out. Then the moment of inertia actual. Okay, so this is a simple network you can see. So 1, 2, 3, 4, 4 hidden things are there, and output layer is the deflection actual. So deflection at 0, 1 meter. We have divided it into 10. This one at every meter say we have to find out the deflection actual. So now what we have done here is a simple data say. This equation you find out for variety of deflection values, Young's modulus I. So these are the inputs W, E, and I. Span is fixed actually. Okay, so you generate data set and then you run it in the MATLAB. So this is a simple code which you can write it in the MATLAB. So you can see the input nodes are 3, that is W, E, and I. Target is a delta, that's a deflection at 10 points actually. Okay, so this is the input, this is the target. You can see in MATLAB how simple. Now this is 11-bar marketed algorithm I have used. So train FCL. Then the hidden layer size say is a 4. So 4 neurons are there actual. Okay, so these are the 4. So you give these inputs to say then net. So this does you the fitting actual. So this once you give this commands a fitnet or whatever, so it does all the it designs the network itself. Now after that what to do, as already I told you have to do 70, 15 and 15 actual. Okay, so training set, then the testing validation set, then of course the testing set itself you have. So training, validation and testing, you divide the data into percentage also. And then this is the commands which trains the network actually. So training means you are finding the weights and biases actually. Okay, so these are very simple commands in MATLAB, and if you plot the network, so view net, if you use this command, you will get the beautiful network. You can see input is 3 inputs are there, hidden layer you are having 4 this one. So you have weights and you have biases also. Then output layer has 11 are there actually. That is a deflection at 0 to 10 meter at every 1 meter, 1 meter, 1 meter, the deflection and the weights and biases. So you just run the network, say automatically you can see that this is your analytical expert. This anyway is just a tie problem. For this, no neural network is not all required also, just a tie problem, So deflection is this one, and this is from the neural network actually. You can see exactly, it matches with this one. Of course, the problem is also very simple. So you get a very excellent match from this neural network itself. And if you see here, say, okay, so the number of unknowns, if you want to calculate, can anybody tell me how many number of unknowns are there here? No. You calculate. I have provided the answer also. You just verify. So this is a 3, this is a 4, and here you are having 11 actually. Okay. Yeah. Yeah, so you can type you follow, right? So how many total number of unknowns? So you can see weights are 3 into 4 is this one. Then 11 into 4, these many are the weights actual. Okay. Then the biases are there. So for each output layer we have a bias, and then 4 are there. So total 11 plus 4 is the bias. And if you add all these things, so you will get a total number of unknowns are 71 actually for this problem. So this is a simple code, which of course we will share it with all the participants also. So it's very easy to write it in MATLAB actually. So simply inputs, outputs, if you do say, okay, input and target, you can see how many commands are required. Simply train algorithm, network size, and that is divide this ratio, and simply you have to train this one. So just within, some 5 to 6 lines, say, you can generate your own network and you can do your calculations also. Extremely simple. Okay. So now anyway, so I have shown you for the toy example. Now coming to this earthquake engineering, say. So now as already I told you from the, for a practicing engineer, say, we want spectral acceleration. That is a response spectra. This is a design value. Okay. So this is what is required actually. So this is what we are calling as response spectra. So this is required in design to design my structure, the site specific spectra or whatever this one. Now this I have to obtain from the data. Okay. So now this NGA West 2 data I'm showing you here. So this data is valid for shallow active regions. So for the shallow active regions, say, okay, so this data set can be used here. So I have already shown you some 13,500 data, which is coming from 288 earthquakes. So this is a huge database which is available. Now I also told you in the starting, people have already developed some empirical equations actually, but the problem was they had 800 to unknowns was there. Okay, so 800 unknowns was there in their model, that C1 plus C2 plus C3 I showed you in the starting, and the sigmas were also very high actually using the conventional approaches. Now the question is, can I model this data with a neural network with very less number of unknowns, and the error also should be less compared to this model? So that is a question which we are asking actually. So now here my inputs are like this. Okay, so magnitude, distance, site condition, which is that VS30. Then we have the fault type. Okay, whether it's a reverse fault or a strike slip fault or thrust fault kind of things itself. So these are the inputs. Now my output is the spectral acceleration actually at several natural periods. So generally, it will go from 0.1 second, 0.01 seconds to 10 seconds. The data goes. So we have sampled it at 28, the natural time period. These are the standard actual. Okay, you can get it from the codes how these natural periods have to be selected. So this is what you see we have to plot. And the challenge is we should be able to, your network should be able to, it should be superior compared to the existing conventional approaches. That means the number of unknowns should be less and sigma also should be less compared to the conventional approaches. So this is our challenge. So now before going to do these type of problems, generally what we do is whenever you have the data, you compute its all the parameters like mean, standard deviation, skewness and kurtosis and all other things. The reason is, whether the data is, whether you are, if you want to have a really, a neural network or not. So this has to be checked actually, whether ANN is required or not. Okay. So ANN is non-linear basically. So if we can solve the problem by linear set, then why you require ANN? It's a waste of our time and resources itself. Okay. So now if you see the mean values for magnitude, the input mean is this one, skewness is 0.501 and kurtosis is 1.801. Now if you see the spectral acceleration data, say 0.01 second, 0.02 second, you see the kurtosis values are extremely high actual. So can any of you know for normal distribution, say what is the skewness and kurtosis? What should be the value? Do you have an idea? See, like for normal distribution means perfect like this actual symmetric distribution. So for normal, say what should be the skewness value? See the data analysis we do. So whenever you want to have the data, say if it is normal, what should be the skewness? That is the third moment. Fourth moment is kurtosis actual. So what should be the value? Can you read here? So skewness is, and what is the value of kurtosis? So you can read the values also. You can just, you will see that one. Now what is the values for normal distribution? What is a pure normal? Skewness has to be. See, all of you are there, right? Voice is audible, no? Yes, all of you are there. Now tell me what's the value of, okay, your voice is audible. So skewness has to be 0 and kurtosis has to be 3 actually, okay? So if skewness is 0 and kurtosis is 3, say, that means the data is, the normal distribution. So if all the parameters are normal distribution, say, then no need to do, neural network actually. You can as well as go for linear regression only. But now here for the data, say, what is the kurtosis values? So these are the inputs actually. Up to this, these are the inputs. Sorry, up to this one is the input basically. Now for the outputs, say that is a PGA, PGV, PGD. What is the kurtosis value? Can you read here? What is the minimum kurtosis and maximum kurtosis for the outputs? So you can type it in the chat box also. Okay, what are the kurtosis values? They are high, or what is that actually? They are very high and they are extremely higher than 3 actual. So that means, so this data set is non-Gaussian actual. Okay. So these are all non-Gaussian. Okay. So that means they are not normal. So if they are not normal, say, that means, you can use your neural network. So this is the first check actually, whenever you want to do to a data set. So you find out all the movements and you check the skewness and kurtosis. And if skewness is no way 0, you can see here also. So the skewness is not 0 and kurtosis is nowhere close to 3. That means data is non-Gaussian and you have to use a non-linear, the techniques itself. Okay, so now this we have to do. So now here one more thing when you do with earthquake data say, so we have to do what we call as mixed effects regression actually. You can't do, a straightforward, just you cannot do the regression. Because the reason is here when the data is coming from different groups say, that means here if you see this figure say, so we are having data from variety groups. Like for example, this is one earthquake actual. Okay, so the data is here basically. So now you are having one earthquake say, so that data will be here itself. So what happens here is when you are having 3 magnitude earthquakes, the stations same only. Suppose all the stations are located in that area. So let us say this is my all the stations are located here say. Okay. And let us say earthquake occurs here. So these are epicenter actual. So now these are all the stations. Now suppose if it is a 3 magnitude earthquake, say what happens for 3 magnitude earthquake? Can you record the earthquake at 1000 kilometers? So the station is 1000 kilometer distance. This station is at 1 kilometer. This station is at 500, 300 say. So when the earthquake is small magnitude say, so what happens? Can you record at 1000 kilometers also for 3 magnitude? Can you record the vibration? Yeah, so you can type it in the chat box or you can ask also. Okay, you can no, fine. Saloni has said no. So you can't record up to 1000 kilometers. So that means for 3 magnitude, although the network is same, you will have records only up to 10 kilometers. This instrument only you have only one record actually. But if it is a 9 magnitude say, then what happens for 9 magnitude? Can you record at all the stations 1000 kilometers also? 9 magnitude. See, 9 magnitude can be felt up to 1000. You can type it in the chat box also. 9 can be, so whether it will be felt at 1000, can you record the data at 500 long distances also? No, just tell me whether you can record it. Yes, it may be recorded. Okay, fine. So, so 9 magnitude can be recorded up to 1000. So what happens is if there are 6 instruments are there, say, for 3 magnitude, you will have only one record only because the nearest one only will record. But if it is 6 magnitude, so maybe you will have 2. Then if it is 7, say 3. Then if it is 8 means 4. Then 9 means 5. So what's happening is as magnitude increases, the network may be same, but the records will be increasing actually. So which means your magnitude and the distances they are correlated actually. So as magnitude is increasing, the distances are also increasing. It is not distance is increasing, but the records is because the effect will go up to that much far away distances. So what happens is M and R are correlations will be there actually among the inputs. Okay. So the inputs generally whenever you are doing a regression, say our assumption is all the inputs should be independent of each other actually. Okay, they should be independent, and of course they are all independent only. But the problem is in earthquakes, say small magnitude, small distance, large magnitude, large distances actually. So MWR, they will be correlated also. Even sometimes VS30 also will be correlated because you have put all your stations on 10 stations on soil and 1 station is in rock say. So that means soil you have more data, rock you have very less data itself actually. So then this also homogenization will be an issue itself. So what we try to do in our cases is we try to do mixed effects regression actually to handle all these MR correlation, then VS30 and all other things we do this way. So I'm showing you an example here. So if you see the data, say what type of trend this data is, if you do least square regression, you will fit this type of a line actually, decreasing line you fit it actually. But here the data is coming from different groups actually. So this color indicates say, so this is one group, this is one group, this is one group actually. So if you see each individual groups, the trend is increasing only. You can see in all the individual groups trend is increasing, but since you have plotted all of them in one graph and try to fit, so you will see a line decreasing trend itself, which is misleading actually. Okay, because of the correlations, because you don't have data and others, you will get wrong pictures when you try to do straightforward regression. So what we try to do is mixed effects regression we do. It's very straightforward, very simple. So this error say, we divide this into two pieces actually, epsilon, this bi and epsilon ij. So these are the parameters. This is your model. And these are the biases actual. So what is inside the group and then group to group and inside the group itself. So we call this as with the inter-event and event residuals we say. Okay. So inter-event say and then inside the event, what is the standard deviation actual? So this is like the standard deviation in this small group and then the overall from this group to this group, say how much is the standard deviation actual. So we divide this into two types of pieces and then do the regression actual. So this is mandatory when you're working with earthquake data. So you will have correlations, not only in earthquake, maybe other types of data also you may face this type of a problem itself actually. Okay. So this has to be done. So this is also one same example for the mixed effects regression. So you can see. So if you do a the mixed effects the ordinary regression say, so this is the line you get actual. Okay. But whereas individual group, you can see the slope of the lines are entirely the different. So when you mix this data, your slope also should match with the group itself. So this is the exact value actual. Okay. So this is the correct one. The other one is the wrong one. So this happens when the data sets are correlated among themselves. So we have to do this mixed effects regression. Okay. So that you can easily do it in the neural network, by partitioning error into two pieces actual. One is inside the group, what is the error? Then from group to group, say what is the error itself actual. Okay. So this is a network I'm showing you here. So the input neurons are 5 actually, 1, 2, 3, 4, 5. Then the hidden neurons we have taken 5. And output are 28 actually. Now you tell me how many unknowns are there in our network actually. Okay. Yeah. So whoever tells means, they have understood the problem correctly. Tell me correctly the number of unknowns in this model. So you will be having a calculator, right, in your computer or you see in the mobile itself. Just calculate and tell me. Somebody said, so how did you get that too? So 5 into 5. Okay, that is from input to hidden plus 28 into 5. That is from the output to this one, plus you have to add biases actual. So 28 plus 5. Calculate and tell me. Total how many unknowns are there? You can type in the chat box. I think somebody said wrong, 281 something they have told. And now tell me what is the total number of unknowns? 305. Just verify. See, 5 into 5 is how much here? 25. Then 28 into 5 is how much? 198. Excellent. I think Saloni Pandey has given the correct answer. So it is 198 unknowns are there. We followed. So this you keep it in mind. So this model has 198, the unknowns in your network itself. Okay. And now this is our expression, the neural network. You can write it in terms of this one. So we take logarithm of all these variables because a PGA is the positive quantities. Okay. So log normal distribution PGA is, so log 10 PGA will be normal, something assumptions are there. So we take this one. So this is our functional form actual. So in neural network, we don't have like C1 plus C2 or something. So this is a functional form actual. Okay. So you can write like this. So you have weights, then biases, then one more bias here. And these weights have to be another weights are there. Okay. So this is from the input to hidden, then hidden to output, and then biases here itself. So this is a functional form for ANN actual. Okay. And then we have to do mixed effects regression itself here. So we have splitted the error into two pieces actually. So this is into something like, intra-event, inter-event, within event, these events are there. So because the data is coming from several groups and M, R, VS30, they may be correlated. So you have to remove all those things itself. And then the functions, a tan hyperbolic function has been used, and F2 say that is the output neuron actual. So that connection is linear, other one is non-linear. You can make both non-linear also, and you have to do all those things. And then also other thing also I told you, so we have to scale all the input parameters because magnitude is from 3 to 8, but whereas distance will go from 0 to 500 say. So you have to normalize them such that all the inputs will be given equal weightage actual. Okay, so do this one. So this is how we do. So what we try to do in our neural network is, so first you have to assume actual. So assume some W1, W2, B1, B2. So this you have to assume actual, okay? And then you run the network say from the response spectra. Then you calculate W1, W2, B1 and B2. And then you calculate tau square and phi square actual. So tau square is nothing but the standard deviation of eta I. That other one is the standard deviation of this group to group error itself, epsilon ij. So this you calculate say. Now once W1, W2, you take this one. So you estimate this between event term and using equation 10 in Abrams, that the procedure is there. And then you give as an input. And then once again, you estimate B1, B2 and fixed effects. You do this calculation iterative way until, the likelihood function or your error say is basically, minimized or what, it will happen actual. So this procedure has to be done actual. So now these are the weights. So these are the optimized, the weights. So this is an optimization after doing this one. So these are the weights. You can see all the weights is minus 0.2248. That is between magnitude and the first neuron actual. So magnitude and the second neurons are 2.18, 3.38 like that. You can see some patterns also. So with the first neuron, it is negative. Other neurons, it is second neuron only, it is a positive actual. Now similarly, VS30 is a first two. You will see, you can, if you want, you can get some physics into the problem also. So this way you will get all the, like if you see the biases here, all biases are negative, negative, negative. So this is from the input to hidden actual. Then from hidden to the output, because hidden we have 5 neurons and 28 are the outputs say, okay. So these are the neurons. So here also you can say PGA, the first one is negative, other things are like that. So you will get all the weights as well as all the biases from your neural network itself, okay. So now we have to plot all the standard plots, like target this one, predicted PGA, how good is the comparisons, what is the R square value, how good well they are correlated also. So this you will easily get it. So as already I told you, we have like a training period, testing period, validation period. So you have to check all the errors in all the three, and all those things one has to do itself. Okay, so this is how we have to. And there are a lot of parameters are there, like R square formula, performance, how much percentage of variance your network experiences, K value, all those things to evaluate how good is your network itself. So if you can find out for all the numbers also, so you can read some of the numbers here. So you can see the correlations, they are almost very, very extremely high. So here also, they are all between the range such which shows that the network is highly efficient actually in capturing the patterns in the data itself. And these are the, you have to plot not only just the numbers, you have to plot the residuals also, okay. So you have to do all those things. You have to plot as a function of magnitude within event, intra-event, inter-event residuals, and all of them should be more or less close to 0 actual, okay. So this is what they expect. And they should not show any pattern at that all. So if it is done, that means your network is has no bias. You have to plot with respect to all the inputs. So one with respect to magnitude, then with respect to distance also, say whether it is showing any pattern. So that means error means it is like a noise. It should not show any pattern. All the pattern should be captured by your the neural network model itself. So you have to verify all these plots also, okay, very rigorously. Not only these numbers, okay, the numbers sometimes they give misinterpretation also. The correlation may be very high, but when you try to look at the data, you will see that there are some patterns your network has not captured. So you have to do all these plots also, and then the numbers also. All of these things have to be verified actually. And these are the standard deviations, which are very important for hazard, the analysis. So you can see we have this inter-event, intra-event, total standard deviation we have. Using measured and VS30 we have done. So these are the total standard deviations actually, okay. Now these are the standard deviations which people have already, estimated using those traditional equations. So these are the things you can see, the standard deviations say, okay. So you can see the standard deviations, these are the values actually. And these standard deviations they have got by taking, something around 400 unknowns, maybe 400 to 800 unknowns. using the conventional approaches, say unknowns was very high, and these are the standard deviations. Now, which is better here? Now in our model, how many unknowns are there? We have calculated, right? 198 unknowns was there. You followed. So number of unknowns in our neural network was less compared to the standard also. Our standard 3, this range we are getting, but whereas they are getting 0.75 or 0.664 like that, you see the standard deviations are extremely high actual. So this means, when the data is so large, say, that means, your neural network is, much superior to traditional, you see the conventional equations or the conventional methods, So this establishes the superiority of the network actual. So when we send this paper also for review, say, so this was the main question actual. So suppose now here why this worked is because the data is large, So if you see the data, say, okay, so it is extremely large. 13,000, I showed you this thing also. So 13,500 data is there. So that's why, your neural network was working very fine. Suppose if you had 1,000 data points, say, the data size is very small actually. So now what is your comment? ANN will be superior or the conventional things will be superior when the data is small? See why in this problem, why ANN worked, why it is superior to the conventional approaches. The data was 13,500. Now, if I ask you the data was only 1,000 data points you take from this graph and then you run the neural network, say, what will happen? So conventional regression will be better, this will be better. Now, what is your comment actually? So this is 13,000, around 13,000 data points. Okay, so 198 unknowns we were able to explain. Same 13,000 data using 400 unknowns or 400 to 800, they were able to get 0.754. Suppose if the data was not 13,000, so what is your comment? Which will be the winner, conventional or the neural network? You can type it in the chat box also, if you are unable to speak. So which is the winner? So the decimal sample size is small, say, which will work? Just a guess, Which will be more efficient when the data is small? Linear only, not linear, maybe the traditional equations only. So in ANN, why it works? The reason is if the data is large, say, your neural network will be more efficient actually compared to conventional things. Okay. Now this also we can do. There is one Garson's algorithm is there to verify the sensitivity of the network actually. So you can identify which is the parameters, say, which controls the data, So which one controls the data, which one more this one. So these are the sense. No, these with respect to the inputs. So this is the magnitude, this one. So this is VS30. Okay, the site condition. Then this is R and this is locked in R actually. Okay, so one indicates geometric damping, other one indicates inelastic damping actually. Okay, and here's a fault mechanism. So you can see the most important parameter, say, is the magnitude actually. So this is the one which controls your data. Okay, among the distance, a log R term, is next comes into picture. 27% is controlled by log R, then R actually. So your site conditions is very small, 6.8% only. Then the fault mechanisms, 5.16 also. So you have to plot the sensitivity also, and we can decide actually. Okay, so which is we can also decide. Suppose in generally in many problems you don't know how many inputs you have to take. Say you take all the inputs, you run your neural network, and then you do this relative importance. If the relative importance is very small, so like less than 1%, then you can delete it that entire thing from the inputs itself also. So that also one can do in our ANN itself. Okay. So this is a very sensitivity. That's a Garson's algorithm or something. We call this one. These are all there in MATLAB. You can just click it automatically. You will get all the numbers also. Okay. So now, and then if you plot, say, how good is the network? So numbers are fine, but whether if you plot, say, whether it will have any, the patterns, like for example, P ground acceleration, say, okay. So now if you plot for 3.5, say 4.5, 5.5, 7.5, say, and if you plot with respect to distance, we all know that as distance increases, PGA should reduce actually. So your neural network, whether it is, you have got a good fit, but whether it works in practice also you have to verify. So you can see the neural network, say, it also shows nicely the pattern. And then in the near the close to the, the very, very close to the fault, say, okay. So this we call as magnitude saturation actually, okay. So irrespective of magnitude, say, the differences will be very, very small actually, okay, 6.5, 5, 6, 7, say, irrespective of the distance, irrespective of the magnitude, the PGS will be magnitude saturation, we say. So that also your neural network has captured actually. You followed. So whatever pattern is in the data, say, automatically it gets captured in our magnitude saturation. And of course, long period things, the magnitude saturation will not be there. So that also automatically the neural network captures all these physical, the phenomenon itself. And if you plot with respect to magnitude, say, so PGA should increase, with respect to magnitude, that also you can observe. And of course, as the magnitude increases, saturation you have to observe actually, okay. That also your neural network, which means, it is like not like a black box, even the physics is not getting violated, say, in our neural network. It has captured almost all the patterns in your input database itself, okay. This is the most important thing. Now if you compare this with the international, that same as already I mentioned you, NGA West equations, okay. So these are all conventional equations based on nonlinear regression. So conventional regressions. So conventional techniques in that 400, 800 unknowns I already told you. So those algorithms, many people have found out actually, Abraham and Son. So these are all the standard NGA West to, the people who has developed these, the equations also. So if you plot all of them, say, in the graph with our developed ANN, so this has been plotted, I think, two magnitudes. One is a 5.5, other one is 7.5. So the top one is for 7.5 magnitude. This is for the 5.5 magnitude actually. If you compare, say, so our developed ANN model, is in the red color. So you can see it almost, it lies within these numbers also. That means, so we are able to capture all the parameters, and sometimes then the error is also less, number of unknowns is also less, and these are much, much superior to the traditional, the conventional algorithms itself, okay. And now this is also the response spectra actually. So now this is for 7.5 magnitude, and this is for 5.5 actual. So this is a 20 kilometer distance, okay, and this is a 250 kilometer at far away places, say. So now how this, and this is for B type soil class, and this is for D type, the soil classes also. So here also this is our ANN, you can see. ANN model is here, and other international equations also I'm showing you. So you can see this is a neural network also, it works fine, but some say in the this region, this gives higher, because these equations have underestimated maybe the value there. So it picks up all the phenomenon, everything, whatever the data, so the patterns, everything is captured by this neural network. And here I am showing you for strike slip. Even if we can plot for thrust fault, reverse thrust, and other things also, the equations, it works very efficiently. It gives you reliable results with less number of unknowns and with less, the standard deviation itself. So this is the most, the important thing which you can get from these models. And then what we have also done is, if I do hazard analysis, so generally, in our earthquake engineering also, many people, although ANN is very powerful and it can have shown you the power of this one also, but ANN, what happens is, but when you want to use it in the practice, okay, that is in the practice, people, they don't have confidence actually, okay, because these are all like a black box or whatever, they say like that. Still they go with the traditional equations also. So what we wanted was, we wanted to show that ANN is also works very nicely if you take it as input in the seismic hazard analysis also, okay. So seismic hazard analysis anyway is a different issue. So you have to give this a GMPA, taking all the faults in this region, and then you could do the hazard calculations, say. So this is our uniform hazard curve. This red one you can see here. So this is the UHRS you will get for Shimla. Okay, we have just done the hazard analysis. So 2,500 return period. So this is what we get. Now, if I use the standard equations, say, you get this type of model itself. So you can see the ANN model which we have developed, say, by taking 500 kilometers around Shimla and doing the hazard analysis. If you use also, you will get the reliable results from our neural network also. So which indicates the confidence actual. So it will increase the confidence in using this ANN based the equations in the hazard analysis also. Okay. So this paper, whatever I have shown you, so this paper is already available. We got published, I think, 2018. So this was the first paper which we did for NGA West 2. Okay, as already I mentioned you, it was reviewed by the NGA West 2 people only. Okay, so if you want to establish the superiority of networks, the challenge is, so you should be able to explain the data with less number of unknowns and with less standard deviation compared to the traditional model. So since we proved all these step by step, the paper got accepted, and then we also showed that if you can use this equation, say, in the hazard analysis also, and you can get some reliable answers from these numbers also. Okay, so this is how this work got completed. Okay, so I think I will stop here. So if you have any questions, you can ask me before we proceed to the next issue. Okay. So any questions if you have on this one, we will discuss right.